having the sun as your neighbour is hard. Searing hot temperatures, deadly radiation, and the onslaught of meteor collisions don't exactly make it the most welcoming part of the solar system. The extreme conditions near our star create an environment so hostile that even the most advanced spacecraft must be specially designed to withstand the brutal assault of solar radiation and intense heat that would vaporize ordinary materials in minutes. The Sun's proximity means that Mercury experiences solar radiation at levels 10 times stronger than what reaches Earth, creating a furnace-like environment that tests the limits of our engineering capabilities. As you can imagine, these challenges make Mercury a particularly tricky place to get to, presenting engineers and mission planners with some of the most difficult obstacles in all of planetary exploration. The technical challenges involved in reaching Mercury are so significant that in the entire history of space exploration, only 3 missions have ever attempted the journey, and only 1 has successfully entered orbit. For this reason, even though it's much closer to us than Jupiter or Saturn, Mercury remains relatively unexplored compared to other planets in our solar system. The proximity to the Sun that makes it theoretically easier to reach also makes it paradoxically one of the hardest destinations to visit successfully, requiring innovative trajectory planning and heat management systems that push the boundaries of spacecraft design. Still, scientists managed to send 2 different missions out to study Mercury, demonstrating human ingenuity and our relentless drive to explore even the most inhospitable corners of our cosmic neighbourhood. These missions represent decades of planning, engineering innovation, and international cooperation, each building upon the knowledge gained from its predecessor. Mariner 10 flew by in the 1970s, providing our first close-up glimpses of this mysterious world and revolutionising our understanding of what had previously been little more than a bright spot in telescopes. The mission performed 3 flybys of Mercury in 1974 and 1975, mapping approximately 45% of the planet's surface and discovering its unexpected magnetic field, which challenged prevailing theories about planetary magnetism. This was followed by NASA's Messenger in 2015, which was the first probe to ever successfully orbit the planet and revolutionized our understanding of Mercury's composition, magnetic field, and geological history in ways that ground-based observations could never achieve. Messenger spent 4 years in orbit around Mercury, far exceeding its planned 1-year mission and returning over 250,000 images, along with vast amounts of data about the planet's surface composition, exosphere, and magnetic environment. And now, as I speak, a 3rd Mercury mission is hurtling through the constellation of Pisces over 177 million kilometers away from Earth, following a carefully calculated trajectory that will eventually bring it to its destination after years of interplanetary travel. Bepi Colombo, a labour of love between the European Space Agency and the Japanese Aerospace Exploration Agency, represents the culmination of years of planning, engineering, and international cooperation between 2 of the world's leading space agencies. The mission is named after Giuseppe Bepi Colombo, an Italian mathematician and engineer who first proposed using gravitational assist to reach Mercury, and whose calculations made the Mariner 10 mission possible. The spacecraft is set to arrive on December 5, 2025, when it will begin its comprehensive scientific mission after a journey of more than 7 years through the inner solar system. It will carry out a comprehensive study of the planet's magnetic field, surface composition, internal structure, and exosphere, providing unprecedented detail about features that have puzzled scientists for decades and answering questions that Messenger's data could only hint at. The mission carries 11 scientific instruments between its 2 spacecraft, each designed to investigate specific aspects of Mercury's environment and history. But as they say, the journey is the destination, and Bepi Colombo's journey is a long one, taking it on a circuitous route through the inner solar system that covers billions of kilometers and requires precise navigation and multiple gravitational assists to reach its final orbit. The complex trajectory is necessary because of the immense gravitational pull of the Sun, which constantly accelerates any spacecraft heading inward from Earth. Without the series of planetary flybys to gradually reduce the spacecraft's velocity, Bepi Colombo would arrive at Mercury with far too much speed to be captured by the planet's weak gravity, and would instead plunge into the Sun. I'm Alex McColgan, and you're watching Astrum. Join me today as we reveal what Bepi Colombo has revealed of Mercury so far, why it's travelling farther than the distance of Pluto to get there, and what we're hoping to learn about the closest planet to the Sun. This mission represents humanity's most ambitious attempt yet to study Mercury in detail, and the discoveries it makes will reshape our understanding of how rocky planets form and evolve in the intense environment close to their parent stars. On October 20th, 2018, Bepi Colombo took off from the French Guiana Space Centre, beginning its 7-year journey to Mercury with a powerful Ariane 5 rocket, providing the initial thrust needed to escape Earth's gravity and set course for the inner solar system. The launch was the culmination of more than 2 decades of planning and development, with the mission concept first proposed in the early 1980s and approved by the European Space Agency in 2000. Its trajectory would take it around the Sun 18 times, including 9 planet flybys that would serve to gradually reduce its velocity relative to Mercury, making orbital insertion possible without requiring impossibly large amounts of fuel that would make the spacecraft too heavy to launch. Each flyby is precisely timed and positioned to provide exactly the right amount of gravitational braking while also allowing the scientific instruments to gather valuable data during these brief encounters with Earth, Venus, and Mercury itself. The first was an extremely close flyby of Earth on April 10, 2020, providing mission controllers with an opportunity to test the spacecraft's instruments on a familiar world and verify that all systems were functioning correctly after 18 months in space. Bepi Colombo came within just 12,700 kilometers of our planet's surface, about the distance from Copenhagen to Santiago, Chile, skimming through the upper reaches of Earth's atmosphere and using our planet's gravity to adjust its trajectory sunward, while also providing spectacular images of Earth and the Moon. The flyby was a critical milestone that confirmed the spacecraft's health and validated the complex navigation systems needed to execute the remaining flybys with precision. Its journey will then take it on 2 flybys of Venus and 6 of Mercury, each one carefully timed to provide the maximum gravitational assist, while also allowing the scientific instruments aboard to gather valuable data during these brief encounters that last only hours but provide irreplaceable observations. The Venus flybys occurred in October 2020 and August 2021, with the spacecraft passing as close as 550 kilometers above the planet's cloud tops and measuring the composition and dynamics of Venus's upper atmosphere. The last 3 Mercury flybys, of which are due to happen in September, December, and January of next year, bringing the spacecraft progressively closer to its final orbital configuration and allowing mission planners to fine-tune the trajectory for the orbital insertion burn. Each Mercury flyby brings Bepi Colombo closer to the planet and reduces its velocity by several hundred meters per second, gradually matching its speed to Mercury's orbital motion. In total, the mighty spacecraft will cover a distance of 8.5 billion kilometers, more than the distance from the Sun to Pluto, making it one of the longest and most complex interplanetary journeys ever undertaken, and demonstrating the extreme measures necessary to visit our nearest planetary neighbour. The circuitous route is a testament to the challenges of spaceflight in the inner solar system, where the Sun's gravity dominates and direct trajectories are impossible for all but the most massive spacecraft carrying enormous fuel reserves. Taking such a long route was the only way Bepi Colombo could slow down enough before approaching Mercury's orbit, as direct trajectories would leave the spacecraft with far too much velocity to be captured by the small planet's weak gravitational field, which is only about 38% as strong as Earth's. But why is slowing down so important, and why can't the spacecraft simply use its engines to brake into orbit the way spacecraft do when approaching Mars or other outer planets? Well, if the spacecraft arrived with too much speed, it would swing right past the planet and get sucked into the Sun's powerful gravitational field instead, potentially ending the mission in a fiery dive into our star, or causing the spacecraft to enter a solar orbit that could never return to Mercury. The Sun's immense gravity accelerates any object falling toward it to tremendous velocities, with Bepi Colombo reaching speeds of over 60 kilometers per second relative to Mercury by the time it arrives at the planet's distance from the Sun. Counteracting this acceleration requires either enormous amounts of fuel or clever use of planetary flybys to gradually shed velocity, and the mission planners chose the latter approach to keep the spacecraft's mass within the limits of the Ariane 5 launcher. The challenge of reaching Mercury is unique among planetary missions, because the spacecraft must not only travel to the planet, but also slow down enough to match its orbital velocity, which is the fastest of any planet in the solar system at an average of 47 kilometers per second. BepiColombo was designed to complement and deepen the findings of its predecessor, the Messenger probe, building upon the foundation of knowledge established by that groundbreaking mission and addressing the questions that Messenger raised but could not fully answer. While BepiColombo carries many of the same instruments as Messenger did, it is equipped with higher caliber tools able to obtain larger ranges of data with greater precision and sensitivity, allowing scientists to answer questions that Messenger's data could only hint at, and to study Mercury in wavelengths and with resolution impossible for the earlier mission. The advances in detector technology, data storage and power systems in the years since Messenger was designed have allowed BepiColombo to carry instruments with capabilities that would have been impossible just a decade earlier. Additionally, Messenger's orbit of Mercury was rather one-sided as Periherm was over the South Pole, meaning we have great detail and mapping of the Northern Hemisphere and almost non-existent data on the Southern Hemisphere, leaving major gaps in our understanding of the planet's global characteristics and making it impossible to determine whether features seen in the north are representative of the entire planet or unique to that hemisphere. This orbital geometry was chosen for Messenger to provide thermal stability and favourable communications geometry, but it meant that the southern hemisphere was largely neglected. BepiColombo plans to rectify this by examining Mercury from an orbital angle, more in line with the planet's equator, providing balanced coverage of both hemispheres and allowing for direct comparisons between the two that will reveal whether Mercury's hemispheres are symmetrical or if there are major north-south differences in composition, geology, or magnetic field strength. The more equatorial orbit will also allow BepiColombo to study regions near Mercury's equator in much greater detail than Messenger could achieve, filling in critical gaps in our knowledge. BepiColombo is a very unique spacecraft. Unlike any other planetary mission previously attempted in the complexity of its design and the sophistication of its scientific payload, it's made up of 3 component parts, 2 probes and a propulsion module, which were launched and travel together in a united configuration known as the Mercury Cruise System run by ESA, with each component serving a specific purpose during both the cruise phase and the eventual orbital operations around Mercury. The Mercury Planetary Orbiter, or MPO, will study the planet's surface and interior, using a suite of instruments designed to map composition, topography, and internal structure with unprecedented resolution and coverage. The MPO carries instruments including spectrometers to measure surface composition, laser altimeters to map topography, cameras for imaging in multiple wavelengths, and a radio science experiment to probe Mercury's internal structure through precise tracking of the spacecraft's orbital motion. These instruments will work together to build a comprehensive picture of Mercury's geology, geochemistry, and internal structure, revealing how the planet formed and evolved over billions of years. While JAXA's Mercury Magnetosphere Orbiter, affectionately known as MEO, will study the planet's suspiciously low magnetic field that has baffled scientists for decades and investigate how it interacts with the intense solar wind at Mercury's distance from the Sun, where the pressure of the solar wind is 10 times stronger than at Earth. The name of MEO was actually chosen by the Japanese general public through a nationwide competition, reflecting the mission's importance to Japan's space program and engaging citizens in the excitement of planetary exploration. It means a waterway, and according to JAXA, it symbolizes the scientific milestones reached so far and wishes for safe travels to come, capturing both the achievements of past missions and hopes for future discoveries, while evoking the flowing nature of the plasma environment MEO will study. MEO carries instruments specifically designed to measure magnetic and electric fields, plasma particles, and energetic electrons in Mercury's magnetosphere, providing a 3-dimensional picture of how the planet's magnetic field interacts with the solar wind and how this interaction changes over time. MEO and the MPO sit either side of an interplanetary propulsion unit called the Mercury Transfer Module, which provides the thrust needed for trajectory corrections and orbital insertion using solar electric propulsion, a highly efficient form of propulsion that uses electricity from solar panels to accelerate xenon ions to high velocities. The Mercury Transfer Module is essential for the mission, providing the continuous low-thrust propulsion needed to fine-tune the trajectory during the cruise phase and to perform the critical orbital insertion maneuver when BepiColombo arrives at Mercury. Stacking the different parts of the craft together like this means most, but not all, of the scientific instruments on board will be inoperative until Bepi-Colombo settles into its orbit around Mercury, as their view is blocked or their operation incompatible with the stacked configuration where the spacecraft function as a single unit. However, several instruments remain active during the cruise phase, including some of the magnetometers and particle detectors, allowing Bepi-Colombo to study the interplanetary environment and the solar wind as it travels through the inner solar system. At that point, the MPO and MEO will be jettisoned from the spacecraft and go their separate ways to study Mercury from different vantage points, with MPO settling into a lower, more circular orbit optimized for surface observations, while MEO enters a highly elliptical orbit designed for magnetosphere studies that will take it from close to the planet out to the boundary where the magnetosphere meets the solar wind. The separation sequence is one of the most critical and challenging phases of the mission, requiring precise timing and coordination to ensure both spacecraft end up in their correct orbits. But don't worry, there's still enough data being sent back to keep us entertained during the cruise phase, as several instruments remain active, and each flyby provides opportunities for valuable science that helps us understand not just Mercury, but also Venus and Earth's magnetospheres. Why don't we take a look back at how far this mission has come, what it's already taught us, and explore some of the amazing things it's seen along the way, from stunning images of Mercury's cratered surface to measurements of its magnetic environment and exosphere that are already revealing surprises. Bepi-Colombo's first encounter with Mercury came in October 2021, marking a major milestone in the mission's long journey and providing the first new data from Mercury since Messenger's mission ended in 2015. Passing just 200 kilometers above the planet's surface, closer than many satellites orbit Earth, it sent back some stunning images that revealed Mercury in unprecedented detail, showing features both familiar from Messenger observations and mysterious new structures never before seen at such close range. As it drifted past at a relative velocity of several kilometers per second, Bepi-Colombo snapped Mercury's northern hemisphere with cameras designed to capture both wide-field context and high-resolution details, providing views that complemented and extended Messenger's coverage of this heavily cratered terrain. To the average person, it might look like our rocky, inert moon, with its grey cratered surface seemingly devoid of activity or interest and resembling a dead world unchanged for billions of years. But the trained eye sees much more than just ancient impact scars. The trained eye sees the Caloris crater, a massive impact basin 1,050 kilometers in diameter that could hold the key to deciphering Mercury's crust composition and understanding the violent impacts that shaped the planet's early history during the late heavy bombardment some 3.9 billion years ago. Caloris is one of the largest impact structures in the solar system, comparable in size to similar basins on the Moon and Mars, and its formation would have had global effects on Mercury's geology and internal structure. The Lermontov crater hosts traces of volcanic activity in mysterious pockets, where an unidentified compound in the planet's crust is being lost to space through some process scientists don't yet understand, and scientists have no idea how or why this process is occurring or what substance is being depleted from these specific locations. The mystery deepens because the loss appears to be ongoing, suggesting active processes rather than ancient history, and understanding it could reveal important information about Mercury's current geological activity. These images remind us just how enigmatic Mercury is, and how much we have left to learn about it despite decades of observation from Earth and previous spacecraft visits that have revealed only a fraction of the planet's secrets. Each new image from Bepi-Colombo raises as many questions as it answers, revealing features that don't fit neatly into our current models of how Mercury formed and evolved. Another camera mounted on the spacecraft caught Mercury from another perspective, one that left the planet's volcanic history on full display and showed regions never before seen at such close range or from such favourable lighting angles. Previously lava-flooded and over 250 kilometres wide, the Haydn crater comes into view along with the Pampa Facula, one of Mercury's many bright spots, probably formed by volcanic eruptions from billions of years ago that vented material from deep within the planet's interior onto the surface where it created distinctive deposits. Even though Messenger had already shown us Mercury's volcanic past through images and spectroscopic measurements that revealed the composition of these volcanic deposits, it's still pretty amazing that this activity left a mark visible after such an inconceivable amount of time, surviving billions of years of bombardment by meteorites and comets and the harsh environmental conditions near the Sun that include extreme temperature variations and constant solar radiation. And Bepi Colombo didn't just show us how the flyby looked through conventional cameras, it captured how the flyby felt in a completely novel way, providing a multi-sensory experience of planetary exploration through creative data visualization that transforms abstract measurements into something humans can directly experience. You know how your phone has an accelerometer in it that helps it know when and how its orientation changes, allowing it to rotate the screen or track your movement for fitness apps and games. Scientists mounted a similar accelerometer on Bepi Colombo's MPO that was far more sensitive and precise than anything in a consumer device, capable of detecting accelerations millions of times smaller than the pull of Earth's gravity. It measured the movements and vibrations of the spacecraft as it flew past Mercury with exquisite precision, detecting tiny accelerations and jolts caused by various forces acting on the spacecraft, including solar radiation pressure, gravitational variations, and the orientation changes needed to keep instruments pointed at their targets, creating a sort of sound map of the flyby that would otherwise be impossible to experience directly since sound cannot travel through the vacuum of space. Scientists then plotted that data to frequencies us humans can actually hear, translating the spacecraft's physical experience into audio that our ears can process and our brains can interpret, creating an auditory representation of the flyby that makes the abstract data tangible and emotionally engaging, so you can actually hear the flyby in a way that makes the abstract data tangible and emotionally engaging, bringing the experience of interplanetary exploration to life in a format that doesn't require specialized scientific training to appreciate. Pay attention to the two distinct sounds towards the beginning of the recording that mark dramatic changes in the spacecraft's environment. They represent the changes in solar radiation pressure when the spacecraft enters and then exits Mercury's shadow, as the constant push of sunlight that accelerates the spacecraft away from the Sun suddenly disappears and then returns, creating audible thunks in the sonified data. The transition is remarkably abrupt because Mercury has virtually no atmosphere to gradually dim the sunlight, creating a sharp boundary between full illumination and complete shadow. The big clunk towards the end is the sound of the Phoebus instrument assuming its parking position, folding back into its protective configuration after completing its observations of Mercury's exosphere during the brief close approach. The resulting audio is both scientifically valuable, for understanding the forces acting on the spacecraft, and strangely beautiful, turning raw data into something that speaks to our human experience and makes space exploration feel more immediate and real. The sonification reveals patterns and events that might be overlooked in traditional graphical presentations of the data, demonstrating the value of presenting scientific information in multiple formats that appeal to different human senses and cognitive processes. And that's not all Bepi Colombo captured during this historic encounter with the innermost planet. Bepi Colombo captured magnetic field data during its flyby that was also later deciphered and sonified by scientists on the ground, providing another layer of understanding about Mercury's interaction with its environment and the complex dynamics of its magnetosphere. This one is a little more abstract than the accelerometer sonification, requiring more explanation to understand what the different sounds represent, but we'll give it a go and try to understand what we're hearing and what it tells us about Mercury's magnetic environment. You're going to hear two synthesizers at the same time, each representing different aspects of the magnetic field environment that Bepi Colombo passed through during its close approach. The first synthesizer changes pitch with the changing magnitude of the background magnetic field, providing a baseline sense of the overall magnetic environment and how it varies as the spacecraft moves through different regions. A lower pitch means more intensity in the magnetic field, indicating regions where Mercury's magnetosphere is stronger or where solar wind is compressing the field against the planet's surface, creating areas of enhanced magnetic pressure. The second synthesizer changes pitch with the variations of the magnetic field magnitude, capturing the turbulence and fluctuations rather than the overall strength, revealing the dynamic nature of Mercury's magnetosphere. A more turbulent magnetic field is represented by a faster change in pitch, creating a more chaotic and unsettling sound that reflects the violent interactions between Mercury's magnetic field and the solar wind. The dotted vertical line shows where the closest approach was, marking the moment when Bepi Colombo passed nearest to Mercury's surface at just 200 kilometers altitude. After the closest approach, you'll hear something that sounds like a DJ scratching a disc, with lots of fast changes in pitch, creating a distinctive rhythmic pattern that immediately stands out from the smoother tones heard earlier in the recording. That right there marks when the spacecraft crosses the magnetosheath, where the magnetic field is highly turbulent as the solar wind crashes into and flows around Mercury's magnetosphere like water flowing around a rock in a stream, creating a chaotic boundary region where magnetic fields reconnect and particles are accelerated to high energies through processes scientists are still working to understand. The magnetosheath is one of the most dynamic and complex regions in Mercury's space environment, where the supersonic solar wind is suddenly slowed and heated as it encounters the obstacle of Mercury's magnetic field, and the sonification makes this transition audible in a way that conveys its dramatic nature. On June 23, 2022, just over halfway in its planned journey to Mercury, Bepi Colombo crossed paths with Mercury once again for its second close encounter with the planet, this time approaching from a different angle that provided views of features not well observed during the first flyby. This time, the spacecraft turned its gaze towards Mercury's largest impact crater, Caloris Basin, a feature so massive it dominates one entire hemisphere of the planet and is visible from Earth through large telescopes under favourable conditions. At a whopping 1,550 kilometres wide, larger than the state of Texas, it's actually one of the widest known craters in the solar system, comparable to some of the largest impact structures on the Moon and Mars, and representing one of the most catastrophic collision events in the inner solar system's history. Caloris Basin was likely created by the collision of a comet, asteroid, or other celestial object some 3.9 billion years ago, during the period known as the Late Heavy Bombardment, when the inner solar system was still being cleared of debris left over from planetary formation, and massive impacts were relatively common. The impact that created Caloris released energy equivalent to trillions of nuclear weapons, instantly vaporizing the impactor and excavating a hole in Mercury's crust more than 10 kilometers deep. The highly reflective lava craters on its floor make it easy to see as the bright semicircular area of Mercury's disk, below the magnetometer boom in Bepi Colombo's images, standing out against the darker surrounding terrain that was not flooded by volcanic lava. The lava flooding occurred hundreds of millions of years after the initial impact, as Mercury's interior was still geologically active and magma could find its way to the surface through cracks in the fractured crust. The second flyby gave us beautiful images of Mercury's craters like we'd never seen before, with lighting conditions and viewing angles that revealed details invisible to Messenger and showed the three-dimensional structure of crater walls and central peaks in stunning clarity. Like this one of Heaney, a crater embedded in smooth volcanic plains potentially near an ancient volcano, which Bepi Colombo plans to examine when it finally settles into orbit, using its full suite of instruments to determine the crater's age through crater counting techniques, its composition through spectroscopic analysis, and its relationship to the surrounding volcanic features that suggest a complex history of impact and volcanic activity. The crater's location within smooth plains suggests it formed after the volcanic flooding that created those plains, making it relatively young by Mercury standards, perhaps only 1 billion or 2 years old rather than the nearly 4 billion years age of many of Mercury's features. Almost exactly a year later, on June 19, 2023, Bepi Colombo reapproached Mercury from a height of just 236 kilometers, coming even closer than previous flybys and providing the highest resolution images yet of Mercury's surface features. The flyby images captured the 600-kilometer-long Beagle-Rupes, one of the many Lobot scarps on Mercury that was first imaged by Messenger in 2008 but never seen in such detail or from such favourable viewing geometry. Beagle Rupes is a massive cliff that rises up to 3 kilometers above the surrounding terrain, created when one section of Mercury's crust was thrust upward and over another as the planet contracted during cooling. Other than our Moon, Mercury is the only planetary body in our solar system known to exhibit this tectonic signature of global contraction, making it a unique laboratory for studying planetary cooling and the tectonic processes that result from that cooling. When the interior of a planetary body cools over billions of years, the planet shrinks slightly and its surface must accommodate this change. It leads to a global contraction and surface expression of a thrust fault, also known as a Labat scarp, where one section of crust is pushed up and over another in a process similar to how mountains form on Earth. but operating on a global scale rather than being localized to specific tectonic boundaries. Beagle Rupes has an especially pronounced curvature, more so than other scarps on Mercury, curving across the surface in a great arc that suggests unusual stress patterns in Mercury's crust when it formed, offering geologists a rare insight into the planet's tectonic history and the stresses that shaped its surface as it cooled and contracted. The pronounced curvature might indicate that Beagle Rupes formed along a pre-existing zone of weakness in Mercury's crust, perhaps related to the Caloris Basin impact that would have fractured the crust on a global scale. As a result of the third Bepi-Colombo flyby, a large 218-kilometre-wide peak ring impact crater received the name Manly after 20th century visual artist Edna Manley, honouring her contributions to Jamaican culture and art and continuing the tradition of naming Mercury's features after artists, musicians and writers. The original basin floor was flooded by lava that erupted from beneath Mercury's crust sometime after the impact, giving the crater its visibly smooth interior texture that contrasts sharply with the rougher terrain surrounding it, where the original surface remains exposed. The lava flooding is evident from the flat floor and the embayment relationships where the smooth lava meets the crater walls. And spectroscopic analysis will reveal whether this lava has the same composition as volcanic deposits elsewhere on Mercury. Bepi-Colombo will explore Manly Crater further from orbit when it settles into its final configuration, seeking to measure its carbon composition and detect other minerals that may be present in order to learn more about Mercury's geological history and the volcanic processes that filled the crater floor after the initial impact excavated it. Understanding the composition of volcanic deposits like those in Manly will help scientists determine what Mercury's mantle is made of and how magma generation and eruption processes worked on Mercury compared to other terrestrial planets. Gliding past Mercury on its most recent flyby in September 2024, Bepi-Colombo snapped a series of farewell Mercury images that captured the planet in stunning detail before it continued on its trajectory around the Sun. At 236 kilometers from the surface, barely higher than the International Space Station orbits above Earth, Bepi-Colombo appears to hug the planet goodbye, with Mercury filling the frame in images that highlight both familiar features like Caloris Basin and new mysteries in regions never before seen at such close range. Scientists back home on Earth will have to wait another 16 months for the next set of images after this most recent flyby, but the data from this encounter will keep them busy analysing and interpreting the findings, searching for patterns and anomalies that might reveal new insights into Mercury's nature. Now, these flybys are more than an indulgence for our senses or opportunities for beautiful photography that can be shared with the public. They also revealed important nuances of the planet's particle environment and magnetic boundaries, providing crucial measurements that fill gaps in our understanding of how Mercury interacts with the solar wind, and how that interaction changes as Mercury moves through different regions of the inner solar system during its eccentric orbit. One of the instruments aboard the MPO probe is Phoebus, standing for Probing of Hermian Exosphere by Ultraviolet Spectroscopy, a sophisticated instrument designed specifically to study Mercury's tenuous atmosphere by European scientists working with Japanese colleagues. Phoebus uses UV emission from Mercury's exosphere, the planet's outermost and only atmospheric layer, to determine its composition, structure, and interactions with the surface, tracking how atoms and molecules move from the surface into space, and how this process changes with location, time of day, and distance from the Sun. It does this by detecting specific types of light emissions in the ultraviolet spectrum, ranging from 55 to 350 nanometers, wavelengths invisible to human eyes but rich in information about atmospheric composition because different elements emit light at characteristic wavelengths when energized by sunlight. By capturing these light emissions across the whole spectrum simultaneously, it helps us figure out what the exosphere is made of and how its particles are spread out vertically and horizontally, revealing the dynamic processes that create and destroy this fragile atmospheric layer that is constantly being replenished from the surface and lost to space. As Bepi-Colombo emerged from Mercury's shadow during one of its flybys, passing from complete darkness into brilliant sunlight in a fraction of a second. Phoebus detected the presence of hydrogen and calcium atoms in the exosphere, confirming earlier findings from MESSENGER that established the presence of calcium in the planet's exosphere, particularly around the equator and on its night side where temperatures allow certain elements to remain temporarily, before being lost to space through photoionization or solar wind sputtering. Interestingly, this is the opposite of the distribution observed for sodium and potassium, which more readily concentrate around the poles rather than the equator, suggesting different source mechanisms or loss processes for different elements in Mercury's exosphere that depend on temperature, solar radiation intensity, and the local magnetic field configuration. The calcium appears to be concentrated in regions where it can more easily escape to space, while sodium and potassium accumulate in cooler regions where they can survive longer before being ionized or blown away. Once in orbit around Mercury in late 2025, Phoebus will be able to send back much more detailed analysis of Mercury's exosphere composition and dynamics, including how it changes with location and time, revealing daily variations as Mercury rotates, seasonal variations as Mercury's distance from the Sun changes during its eccentric orbit, and even variations tied to solar activity that might reveal how coronal mass ejections affect Mercury's tenuous atmosphere. These measurements will be compared with similar observations made by MESSENGER to look for long-term changes in the exosphere that might indicate evolving conditions on Mercury or variations in solar activity between the two missions. Speaking of MESSENGER, back in its day during its 4-year orbital mission, it discovered ice on Mercury's North Pole, finding radar-bright deposits in permanently shadowed craters that could only be explained by the presence of water ice, because no other substance matches both the radar properties and the thermal stability requirements. Bepi Colombo will continue this legacy by continuing the search for ice in permanently shadowed regions of high-latitude craters, using instruments that can detect water in different ways and at different wavelengths to build a complete picture of Mercury's ice deposits, including their thickness, purity, and extent. The discovery of water ice on Mercury was one of MESSENGER's most surprising findings, because Mercury seems like the last place you'd expect to find ice, but the permanently shadowed crater floors near the poles are cold enough to preserve ice for billions of years, never receiving direct sunlight and remaining at temperatures below -170 degrees Celsius, where water ice is stable even in vacuum. Understanding how much ice is present and where it came from will help scientists understand the delivery of water and other volatiles to the inner solar system during planetary formation, and might even have implications for future human exploration if we ever develop the technology to send astronauts to Mercury. As you might know, Mercury is the only planet in our solar system besides Earth to have a magnetic field similar to Earth's dipole configuration, with clear north and south magnetic poles aligned roughly with the planet's rotation axis. Thanks to its liquid iron core, Mercury exhibits a dynamo effect, which creates an innate magnetic field around the planet through the same mechanism that powers Earth's magnetic field. Convection of electrically conducting fluid in the planet's core generates electric currents, which in turn generate magnetic fields. However, Mercury's magnetic field is just 1.1% that of Earth's magnetic field, about 100 times weaker, leaving scientists fascinated with how it's generated and why it's so much weaker than Earth's, despite Mercury having a similar internal structure with an iron core taking up a larger fraction of the planet's volume than Earth's core does. The weakness of Mercury's field might be due to its slow rotation, taking 59 days for each spin compared to Earth's 24 hours, or it might reflect different conditions in Mercury's core such as composition, temperature, or the presence of a solid inner core. One of the big goals of the Bepi Colombo mission is understanding this magnetic field better through comprehensive mapping it in 3 dimensions and tracking how it changes over timescales ranging from seconds to years to reveal the processes generating and maintaining it. So far, only the magnetic activity of the Northern Hemisphere has been mapped in detail by NASA's MESSENGER mission due to its polar orbit geometry, leaving the Southern Hemisphere largely unknown and creating uncertainty about whether Mercury's magnetic field is symmetric or has major north-south asymmetries. Scientists hope that Bepi Colombo will be able to shed light on the dynamics of the planet's magnetism in the Southern Hemisphere, revealing whether the field is symmetric or if there are major north-south differences in strength, structure, or dynamics that would provide clues about the dynamo process operating in Mercury's core. This magnetic field is of great importance for understanding Mercury's history and evolution because magnetic fields are generated by core dynamos, and the characteristics of the field tell us about conditions in the core. By understanding Mercury's magnetic field in detail, scientists aim to shed light on Mercury's origins, its evolutionary journey from a molten protoplanet to the cooled world we see today, and the current state of the planet's interior, including whether the core is partially or fully liquid, whether it has a solid inner core like Earth does, and how heat escapes from the core to drive the convection that powers the dynamo. MPO and MEO will travel through different areas of Mercury's magnetosphere on different timescales, with MPO sampling the low-altitude regions close to the planet where Mercury's intrinsic magnetic field dominates, while MEO explores the outer magnetosphere and its interaction with the solar wind at altitudes where the solar wind pressure becomes important, simultaneously measuring how the magnetic field changes over time and space and its relationship to the powerful solar wind that constantly buffets Mercury at pressures 10 times greater than the solar wind pressure at Earth. All this new data from the Bepi-Colombo mission will eventually be compared with global magnetic field models from the Messenger mission to build the most accurate picture yet of Mercury's magnetic field, combining measurements from 2 different orbital geometries and time periods to create a comprehensive model that could unlock telling insights into the planet's elusive past and help us understand how small planets generate and maintain magnetic fields despite having cooled significantly since their formation. As we await Bepi-Colombo's next flyby in September 2024, the journey to understanding Mercury continues, with scientists eagerly anticipating each new dataset and planning how to analyze the unprecedented measurements that will come when the spacecraft finally enters orbit. The spacecraft is gearing up for its next major maneuver, a prolonged solar electric propulsion thruster arc planned to begin in early August, and it should last until mid-September, during which the spacecraft's ion engines will fire continuously to slowly reduce its velocity by accelerating xenon ions out the back of the spacecraft at high speeds. Thruster arcs along with strategic flybys help Bepi-Colombo brake against the enormous gravitational pull of the Sun, fighting the star's gravity through a combination of planetary assists and careful thrust management that must be precisely calculated to bring the spacecraft to Mercury with exactly the right velocity for orbital insertion. This is the only way to successfully insert into orbit around Mercury when the time comes, as no single maneuver could provide enough deceleration to slow the spacecraft from its high velocity relative to Mercury to the much lower velocity needed for capture into orbit. Once in orbit in December 2025, the real exploration begins with both MPO and MEO operating simultaneously, with both spacecraft operating simultaneously, to provide unprecedented coverage of Mercury and its environment from 2 different orbital perspectives that will reveal how conditions change with altitude and time. Mercury's heavily cratered surface records a 4.6 billion-year history of asteroid and comet bombardment, preserving a record of impacts dating back to the planet's formation and the late heavy bombardment that sculpted the surfaces of all terrestrial planets, which together with unique tectonic and volcanic curiosities will help scientists unlock the secrets of the planet's place in solar system evolution and understand how rocky planets form and change over billions of years. Bepi-Colombo is set to remain in orbit around Mercury for 1 year, completing multiple Mercury years during that time since Mercury's orbital period is only 88 Earth days, and if all goes well might get the green light for an extra year on the mission as Messenger received, potentially doubling the amount of data returned and allowing for study of how Mercury changes over different seasons and solar conditions, including variations in solar activity that affect the magnetosphere and exosphere. Scientists hope to study the planet like never before, with resolution and coverage far exceeding anything Messenger could achieve due to advances in instrument technology and the dual spacecraft approach. From its composition to its geophysics, from mapping the distribution of elements across the surface to probing the structure of the interior through radio tracking and gravity measurements. Its atmosphere and magnetosphere will be studied comprehensively with instruments designed to measure everything from neutral atoms to energetic particles, both its history recorded in the geological record and the history of other inner planets like it, including Earth, by using Mercury as a laboratory for understanding terrestrial planet evolution. Until then, we've got a few more flybys to look forward to, and the haunting pictures they're bound to capture for us Earthlings back home, each one revealing new wonders and raising new questions about this enigmatic world closest to our Sun, reminding us that even the planets we think we know can still surprise us. Mercury is doing something weird right now that challenges our preconceptions about what planets can do. Imagine yourself standing on the surface of Mercury, though you would need an extremely advanced spacesuit to survive the extreme conditions, but not the Mercury you usually picture when you think of this small rocky world baking in the sun's glare. Not the scorched, sun-blasted daytime inferno where temperatures reach over 400 degrees Celsius, hot enough to melt lead and zinc. Instead, you're here during the planet's incredibly long night that lasts for 88 Earth days, an entire Mercury year. The sun set weeks ago, and it won't rise for weeks more as Mercury slowly rotates on its axis. Above you, the stars are stark and brilliant against a perfect black sky, untouched by atmosphere haze since Mercury has virtually no atmosphere to scatter starlight or create the familiar glow we see on Earth. The ground beneath your heavily insulated boots is rigid, radiating away the day's heat into the vacuum of space through thermal radiation, the only way heat can escape in the absence of an atmosphere. It's a silent, desolate landscape where no sound can travel and the only motion comes from the occasional meteorite impact in the distance. But tonight, you've brought special equipment, not just for survival in this extreme environment, but for observation of a phenomenon that wasn't even known to exist until the 21st century. You point a sensitive detector tuned to a specific wavelength of light towards the anti-solar point in the sky, the direction directly opposite where the sun lurks below the horizon, hidden from view but still dominating Mercury's existence through its immense gravity. And you see it through your instrument, something faint, ethereal, almost unbelievable given Mercury's reputation as a dead world. Stretching away from the planet, reaching impossibly far into the blackness, is a ghostly elongated glow that extends millions of kilometers into space. It's a whisper of light invisible to the unaided human eye, requiring specialized filters and sensitive detectors to observe, a delicate structure millions of kilometers long trailing behind this tiny battered world like the train of a spectral gown flowing across the blackness of space. Mercury, the seemingly inert little rock closest to the sun that most people dismiss as uninteresting, is doing something deeply strange in the dark that reveals the planet is far more dynamic than it appears. It's venting a tail into space, streaming material out into the solar system in a continuous flow. A tail made not of gas or dust in the way we usually think of comet tails with their mixture of water vapour, carbon dioxide and rocky particles, but of something far more specific and intriguing that tells us about the unique processes operating on Mercury. Sodium atoms ejected from the surface and swept into space by solar radiation pressure. I'm Alex McColgan and you're watching Astrum. Join me today as we delve into one of the solar system's more subtle and surprising phenomena, the vast invisible sodium tail of Mercury that stretches millions of kilometers into space. We'll explore how this bizarre feature was discovered through patient observation and specialized instruments, investigate the complex processes that create and shape it through the interaction of Mercury's surface with the solar wind and solar radiation, and understand what this ghostly appendage tells us about the innermost planet and its relationship with the sun that dominates its environment. When we think of planets with distinct features, Mercury rarely comes to mind as anything special. It's the runt of our planetary family, the smallest planet since Pluto's demotion to dwarf planet status in 2006. A tiny cratered world baking in the sun with no moons, no rings and barely any atmosphere. But in 2001, everything changed when a team of astronomers made a discovery that would transform our understanding of Mercury. Scientists have been using specialized sodium filters to observe Mercury since the mid-1980s, when sodium was first discovered in the planet's exosphere through ground-based spectroscopic observations. That's exactly what the team at McDonald Observatory in Texas were doing when they spotted something strange that didn't match their expectations. A faint glow extending far beyond Mercury's tiny disk, stretching across the sky in a direction away from the sun. Initially, they didn't believe their own eyes because the observation seemed too extraordinary to be real. They thought it must be the result of an equipment malfunction, or data processing errors, perhaps a reflection or scattered light creating a false signal. But after thoroughly checking and double-checking their equipment, their calibration, and their data reduction procedures, the astonishing truth emerged that this was a real feature of Mercury. Mercury was trailing an enormous structure through space, a phenomenon never before observed around a planet, a tail of sodium stretching almost 2.5 million kilometers behind it, longer than the diameter of the Sun itself. For perspective, that's 700 times the width of Mercury itself, which has a diameter of only 4,080 kilometers, and the tail could stretch from Earth nearly to the Moon 6 times over. The discovery was humbling and reminded astronomers that despite centuries of observations, the solar system can still surprise us. Mercury isn't some distant, obscure object on the edge of the solar system like Neptune or the Kuiper Belt objects. It's one of our closest cosmic neighbours, visible to the naked eye since prehistoric times and known to ancient civilizations who tracked its motion across the sky. We've been observing it since ancient times with ever-improving telescopes, and even visited it in the 1970s and the 2000s, thanks to NASA's Mariner 10 and Messenger spacecraft that photographed its surface and measured its composition. And yet, this colossal feature remained completely undetected until the 21st century, despite Mercury being one of the most observed objects in the night sky. Hidden in plain sight because it requires very specific observing conditions and specialized equipment to detect. The discovery was a big deal because it challenged our classification of what can have a tail in our solar system and forced scientists to reconsider the boundary between planets and comets. Suddenly, Mercury wasn't just a bland cratered world resembling a slightly larger version of the Moon, but a planet with a dynamic feature rivaling the most spectacular comets, demonstrating that planets can exhibit comet-like behavior under the right conditions. So, how is Mercury's tail different from comet tails that we're familiar with from spectacular apparitions like Halley's Comet or Hale-Bopp? And why would this planet have a sodium tail specifically rather than the water and dust tails we associate with comets? The answer is the fascinating result of Mercury's unique position closest to the Sun, its composition that differs from both comets and the other terrestrial planets, and the Sun's fierce influence that subjects Mercury to environmental conditions unlike anywhere else in the solar system. Comets are kind of like dirty snowballs hurtling through space, compact masses of ice and rock. They are mainly made of water ice along with frozen carbon dioxide, methane and ammonia, which sublimates turning directly from solid to gas as the comet approaches the Sun and heats up, leaving behind a trail of ionized gas and dust particles that create the spectacular displays we observe from Earth. The gas forms an ion tail pushed directly away from the Sun by the solar wind, while heavier dust particles form a curved tail following the comet's orbital path. In contrast, Mercury is a rocky planet with minimal if any ice on its surface where the Sun can reach it. Scientists think there may be water ice hidden in permanently shadowed craters at its poles where temperatures remain below -170 degrees Celsius, but these frozen deposits remain stable precisely because they never receive direct sunlight that would cause them to sublimate and be lost to space. So, Mercury's tail isn't formed through the sublimation of ice into gas as comet tails are, but through entirely different processes. It's made of sodium atoms that have been liberated from the rocky surface. But why sodium specifically, and where does it come from? To understand that we need to take a look at Mercury's proximity to the Sun and the extreme environment that creates. At perihelion, the closest point in its elliptical orbit, Mercury comes as close as 46 million kilometers from the Sun, while at aphelion it recedes to 70 million kilometers, creating a huge variation in solar heating and radiation intensity over the course of Mercury's 88-day year. Where Mercury is exposed to solar radiation up to 10 times more intense than what we receive on Earth, with the solar constant at Mercury ranging from about 6 to 14 times Earth's value depending on orbital position. The solar wind is absolutely torrential at Mercury's distance, much stronger than the gentle breeze that reaches Earth. Imagine a constant stream of charged particles, primarily protons and electrons, flying at 1.6 million kilometers per hour from the Sun straight at you, with nothing to slow them down or deflect them. When those particles strike Mercury's surface at these enormous velocities, they physically knock out other atoms on Mercury's surface in a process called sputtering that transfers momentum from the incoming particle to surface atoms. Picture a bunch of fridge magnets sitting on your fridge in a familiar everyday example of this principle. They don't fall on their own because the magnetic force holds them in place against gravity. But then, say you throw a bouncy ball at the fridge with considerable force. When it hits, the kinetic energy spreads out through the fridge's structure and shakes some of the magnets, transferring energy through the material. If enough energy makes it to the weakest magnet, more energy than is what's keeping it stuck through magnetic attraction, it will pop off and fall down to the floor. That's exactly what's happening in a sputtering collision cascade on Mercury's surface, though at a much smaller scale. Ions from the solar wind shower Mercury at high velocities, creating high-energy impacts that dislodge the weakest link atoms from the surface of the planet through momentum transfer, just like the bouncy ball dislodged the weakest fridge magnet by transferring its kinetic energy. It just so happens one of the most weakly bound elements on Mercury's surface is, you guessed it, sodium, which has a relatively low binding energy compared to the silicate minerals that make up most of Mercury's crust. Messenger data show that during periods of high solar wind activity, when the flux of particles increases dramatically during events like coronal mass ejections, these solar wind particles rain down on Mercury's surface and result in a 50% rise in sodium group ions in the planet's atmosphere compared to quiet periods. This indicates that stronger solar wind activity enhances surface particle interactions, leading to a greater release of sodium into Mercury's atmosphere and tail, providing direct evidence of the link between solar activity and Mercury's exosphere. But there is more to the story than just solar wind sputtering. In addition to solar wind bombardment, Mercury is also tormented by micrometeoroids, tiny particles of rock and metal left over from asteroid collisions and comet passages that fill the inner solar system. And without an atmosphere to slow them down through friction, even dust-sized particles strike the planet with tremendous force, hitting at velocities of tens of kilometers per second and releasing their kinetic energy in violent impacts. These tiny space rocks vaporize surface materials on impact, instantly heating the impact site to thousands of degrees and releasing even more sodium atoms along with other elements into the exosphere where they can be swept away by radiation pressure. We're essentially watching a process of space erosion, observing in real time how planetary surfaces are modified by their space environment. A planet that is slowly disintegrating over billions of years right in our cosmic front yard, losing material to space one atom at a time, though at a rate far too slow to significantly change the planet over human timescales. Some researchers have noticed enhancements in the tail that seem to correlate with times when Mercury is predicted to pass through denser streams of interplanetary dust, like debris from Comet Encke and other comets whose orbits cross Mercury's path, creating temporary increases in the micrometeoroid flux. This would boost the contribution from micrometeoroid impact vaporization, temporarily increasing the amount of sodium injected into the exosphere and subsequently fed into the tail, creating brightness variations that can be observed from Earth. But the shaping of the sodium tail isn't primarily due to the solar wind blowing it back, as is largely the case for a comet's ion tail, which is pushed directly away from the Sun by the pressure of the solar wind particles. Instead, the dominant force sculpting Mercury's sodium tail is solar radiation pressure, a subtle effect that becomes important for small particles. This is a subtle but powerful effect that dominates the dynamics of small particles in the solar system. Photons, the particles of light despite having no mass, carry momentum according to quantum mechanics and Einstein's theory of relativity. When a sodium atom in Mercury's exosphere absorbs a photon of light, it gets a tiny push in the direction the photon was travelling away from the Sun, transferring the photon's momentum to the atom. It then quickly re-emits a photon in a random direction determined by quantum mechanics, causing negligible recoil on average since the emissions are isotropic, meaning equally distributed in all directions. However, the atom is immediately ready to absorb another photon coming from the Sun, and the cycle repeats continuously as long as sunlight is available. This continuous process of absorbing solar photons and receiving tiny directed pushes effectively acts like a gentle but constant wind pushing the sodium atoms away from the Sun, accelerating them over time until they reach velocities of hundreds of kilometers per second. Imagine countless tiny solar sails, each one a sodium atom being persistently nudged by sunlight streaming from the Sun. This relentless pressure accelerates the atoms anti-sunward, overcoming Mercury's weak gravity, which is only 38% of Earth's, and stretching them out into the vast elongated tail structure observed from Earth that extends millions of kilometers into interplanetary space. Because radiation pressure acts directly away from the Sun regardless of Mercury's motion, the tail reliably points in the anti-solar direction, always extending away from the Sun just as comet ion tails do. But as I mentioned, despite being so big in spatial extent, longer than the diameter of the Sun itself, it's not actually visible to the naked eye, because it's incredibly tenuous with atom densities far lower than the best laboratory vacuums on Earth. So, how did scientists spot it, when it can't be seen with normal telescopes or cameras? When sodium atoms absorb energy from sunlight, they become excited, meaning their outermost electron jumps to a higher energy level, entering an excited state that is unstable. When this electron falls back to its ground state after about 16 nanoseconds, it emits a photon at a very specific wavelength determined by quantum mechanics, 589 nanometers, which corresponds to yellow-orange light. Light at this wavelength has a distinct colour you've definitely seen before in everyday life. It's the colour of old street lights, the sodium vapour lamps that cast an orange glow over many cities and neighbourhoods before being replaced by LED lights. This process is happening constantly in Mercury's tail as solar photons excite sodium atoms, and those atoms emit the characteristic yellow light. However, the tail is hidden from the human eye and from standard telescopes because the emission is incredibly faint, drowned out by scattered sunlight and light from other sources. To reveal it, astronomers use specially designed filters called sodium D-line filters that isolate light at precisely 589 nanometers with a bandwidth of only a few nanometers. These filters block all other wavelengths, allowing the faint glow of sodium to stand out against the black background of space like a neon sign in the darkness. By deleting all other wavelengths of light, scientists were able to see the sodium tail emerge from the background noise, revealing Mercury's hidden feature. Mercury's sodium tail varies dramatically throughout its 88-day orbit around the Sun, changing in brightness, length, and structure as Mercury's position and velocity change. The orbit is highly elliptical with an eccentricity of +206, the highest of any planet. When Mercury reaches perihelion, its closest approach to the Sun at 46 million kilometers, the increased solar radiation dramatically intensifies the rate of sodium ejection from its surface through both increased solar wind sputtering and enhanced, photon-stimulated desorption, where solar photons directly liberate surface atoms. You might expect the tail to reach peak visibility at perihelion, since that's where the solar wind and radiation are strongest, by a factor of more than 2 compared to aphelion. However, observations show it actually reaches peak brightness 16 days after perihelion, a surprising delay that puzzled scientists until they understood the physics involved. Let me explain the mechanism behind this delay. Since Mercury's orbit is highly elliptical, its orbital speed also varies a lot according to Kepler's laws of planetary motion, from 39 km per second when it's farther from the Sun at aphelion to 59 km per second when it's closer at perihelion, a 50% variation in speed. Through repeated observations over multiple Mercury years, scientists noticed that Mercury reaches its maximum radial velocity, its speed moving directly away from the Sun rather than perpendicular to the Sun-Mercury line, after slingshotting past the Sun at perihelion, exactly 16 days after perihelion when Mercury is rapidly receding from the Sun. In other words, that's when it's travelling away from the Sun at its top speed of about 10 km per second radially, creating optimal conditions for the sodium tail to extend and become more observable from Earth, because the atoms are being carried away from the Sun by Mercury's motion, in addition to being pushed by radiation pressure. But why would higher radial speed lead to a brighter tail, when the amount of sodium being ejected should depend primarily on solar radiation and solar wind intensity? 2 words explain this counterintuitive phenomenon: Doppler shift. The same effect that makes a train whistle change pitch as it passes. When we look at the spectrum of light from the Sun using a spectrograph to spread sunlight into its component wavelengths, we see dark lines called Fraunhofer absorption lines, named after the German physicist who first studied them systematically. These are wavelengths where certain wavelengths of light are being absorbed by elements in the Sun's atmosphere before the sunlight is emitted into space, creating characteristic patterns that identify the elements present. The Sun's atmosphere contains sodium just like Mercury's tail, and this sodium absorbs all the sodium-specific light at 589 nanometers before the light travels to Mercury, creating an absorption line at exactly the wavelength Mercury's sodium atoms need to fluoresce efficiently. But the faster Mercury travels away from the Sun, the more the sunlight is Doppler shifted or stretched from Mercury's perspective. This means the wavelength gets longer or redder. As the light source and observer move apart, the entire sunlight spectrum is shifted to longer wavelengths, including the Fraunhofer absorption lines that shift away from their rest wavelengths. So the sodium-specific light at 589 nanometers is no longer blocked by solar sodium because the blocking occurs at a slightly different wavelength. and solar radiation at 589 nanometers becomes available for the tail atoms to absorb and scatter back toward Earth. The result is dramatic. The tail gets brighter by orders of magnitude, and we can see it from Earth much more easily, turning an almost invisible feature into something detectable with relatively modest telescopes. So if astronomers wanted to spot Mercury's tail, they just need to look up on day 16 past perihelion with their sodium filters and point their telescopes at Mercury, right? Well, it's not that simple, because multiple conditions must align for successful observations. There are three other main factors at play to consider beyond Mercury's orbital position. Firstly, Mercury must be at a sufficient elongation from the Sun in Earth's sky, at least 15 to 20 degrees away, so that it isn't caught in the glare of the Sun that would overwhelm the faint tail emission even with filters. Secondly, it can't be behind the Sun from Earth perspective, what astronomers call superior conjunction, because then we obviously can't observe it at all, and any tail would be pointed toward Earth, making it invisible. And finally, it must be at the perfect angle for Earth-based telescopes to view its anti-sunward direction, requiring Mercury to be positioned so the tail extends into our line of sight, rather than perpendicular to it. This astronomical alignment only occurs during very specific periods, roughly every few years when all the orbital geometry works out favourably, making observations of Mercury's tail challenging and requiring patient planning. And to think the scientist at McDonald Observatory caught it basically by coincidence in 2001, happening to observe at exactly the right time with exactly the right equipment. Talk about perfect timing and the importance of serendipity in scientific discovery. Some of the most spectacular images of Mercury's sodium tail have come from observatories utilizing coronagraphs, instruments that block the Sun's direct light using an occulting disk, allowing the faint glow of the tail to become visible even when Mercury is relatively close to the Sun in our sky by reducing scattered light. Each successful observation represents a triumph of astronomical planning and precision, requiring clear skies, stable atmospheric conditions, and careful timing. These rare glimpses show a tail that changes dramatically with Mercury's position relative to the Sun, stretching, shortening, brightening, and dimming in a cosmic dance governed by orbital mechanics and atomic physics, revealing the dynamic nature of planet-Sun interactions. But this story stretches beyond Mercury itself and its immediate vicinity. It has provided an unexpected window into key processes occurring throughout our solar system and beyond, helping us understand how stars interact with planets. Firstly, it gives us a glimpse into planetary evolution over billions of years. While the current rate of surface material loss through the tail is too small to significantly alter Mercury in human timescales, losing perhaps only a few hundred kilograms per second, over billions of years this process could potentially affect its surface composition, gradually depleting sodium and other easily liberated elements from the surface layers and altering the chemical makeup we observe today. We could use this knowledge to infer what might have happened to older planets in other solar systems orbiting different types of stars and understand their life cycle better, particularly exoplanets orbiting very close to their parent stars. Secondly, and perhaps most excitingly, the discovery has profound implications for exoplanet research and our understanding of planets beyond our solar system. Many star systems contain hot Jupiters, gas giant planets with masses similar to Jupiter, but orbiting extremely close to their stars, sometimes closer than Mercury orbits the Sun, completing an orbit in just a few days. If Mercury can generate a 2.5 million kilometer tail, despite being a small rocky planet, these giants likely sport even more dramatic features with tails potentially extending tens of millions of kilometers, potentially shedding significant mass through similar mechanisms over their lifetimes, and possibly even affecting the composition of their host stars. The detection methods developed to study Mercury's tail are now being applied in the search for similar phenomena around distant worlds using large telescopes and sensitive spectrographs. By looking for the distinctive spectral signatures of elements being stripped from exoplanets, including sodium but also other elements like potassium, magnesium, and calcium, astronomers may gain new insights into their composition and environment without ever visiting these distant worlds. In fact, we have already detected similar sodium tails or exospheres around our own moon during observations when the moon passes through Earth's magnetotail, suggesting this phenomenon may be common around airless bodies exposed to solar wind and that Mercury is not unique, but rather an extreme example of a common process. Mercury's sodium tail represents a perfect opportunity for studying planet-star interactions throughout the universe, serving as a nearby laboratory for understanding processes that occur around countless other planets. By better understanding this phenomenon through observations and modelling, we gain crucial insights into how stars shape and erode their planetary systems over billions of years, potentially affecting habitability and evolution. Bepi Colombo mission has already completed 6 rapid flybys of Mercury as of 2024, each one providing valuable data about the planet and its environment. It's set to enter into orbit in December 2025, where it will spend at least 1 Earth year studying Mercury's internal composition and its impressive exosphere in unprecedented detail. This will provide data on the sodium tail in unprecedented detail, with instruments specifically designed to study the exosphere, promising new discoveries about this fascinating phenomenon, including how the tail varies with solar activity, Mercury's orbital position, and local time of day on Mercury. The measurements will revolutionize our understanding of how planetary surfaces interact with their space environment, and how material escapes from planets over time. Mercury's elusive tail reminds us that even after centuries of astronomical observation, since Galileo first turned his telescope skyward, fundamental discoveries about our closest cosmic neighbours are still being made, and the solar system still holds surprises. What other secrets might our cosmic neighbourhood still be hiding, waiting for the right instruments and observations to reveal them? The universe never stops surprising us with phenomena we never imagined. All we need to do is keep looking with open minds and innovative instruments, and the cosmos will continue to reveal its wonders. Everyone knows the name of the first planet in our solar system, the one closest to our parent star. Mercury was seen in ancient times by observers from many cultures who tracked its motion across the sky, and carries the name of a Roman god, the fleet-footed messenger of the gods, which seemed appropriate for the planet that moves fastest across the sky. We've known of its existence for thousands of years since prehistoric times when humans first studied the stars. It's not hidden in darkness on the outer fringes of the solar system, but thanks to its position next to the Sun is bathed in brilliant light, receiving more solar radiation than any other planet. And yet, it is the least explored terrestrial planet despite its proximity, having only been visited by 2 probes in all of our spacefaring history, spanning more than 6 decades. Why is that, considering we've sent multiple missions to Mars, Jupiter, Saturn, and even distant Pluto? Is it boring compared to the other planets with their dramatic features? What do we truly know about Mercury beyond its basic characteristics? What are its physical and orbital characteristics and geological history? And how have we learned about it given the challenges of getting there? I'm Alex McColgan and you're watching Astrum, and in watching this comprehensive exploration, you're about to find out everything we know about this fascinating world. Join with me as I teach you everything you might want to know about the first planet in our solar system, Mercury, from its formation billions of years ago to its current state and future exploration. When you think about the physical characteristics of Mercury, I'm sure you imagine it being the closest planet to the Sun with all that implies, but also that it's this giant rock floating in space covered with craters. You wouldn't be too far wrong with that basic description. But it is much more interesting than what you may first think when you dig into the details. For example, when I look at Mercury, I do think of our Moon because they look superficially similar. But Mercury actually is visually more appealing than our Moon with subtle colour variations. Look at it in its true colour as captured by messenger spacecraft. The first thing that I notice is that it actually does have a colour scheme that's more varied than the Moon. It's not just different shades of grey as the Moon appears. And what else makes Mercury unique? Well, did you know, for example, that Mercury consists of approximately 70% metallic material and 30% silicate materials by mass? A very unusual composition for a terrestrial planet. So, it's actually more metallic than rocky, which is the opposite of Earth, Venus, and Mars, where silicates dominate. Because of this unusual composition, Mercury's density is the second highest in the solar system at 5.427 grams per cubic centimetre, only slightly less than the planet with the greatest density, that of Earth, at 5.515 grams per cubic centimetre. If Mercury happened to be the same size as Earth, maintaining its current density, that would mean it would pretty much have the same gravitational pull at its surface as Earth does. but being the size that it is with a diameter of only 1,480 kilometers compared to Earth's 12,142 kilometers, its surface gravity is only 3.7 meters per second squared, about 38% of Earth's. If you were to compare its gravity to Earth visually, it would look something like this. A person jumping on Mercury could leap about 2.6 times higher than on Earth. This means the surface gravity of Mercury is only slightly less than what it is on Mars, which has 3.7 meters per second squared as well. And considering that Mars is a much bigger planet with a diameter of 6,179 kilometers, that just says something about the extraordinary density of Mercury and its metallic composition. But before we leave the subject of Mercury's size, I want to show you one last comparison that surprises most people, that of Ganymede and Titan against Mercury. Now, Ganymede is the solar system's biggest moon discovered by Galileo in 1610, and also the biggest moon of Jupiter with a diameter of 5,268 kilometers, while Titan is Saturn's biggest moon and the second biggest moon in the solar system at 5,150 kilometers, discovered by Christian Huygens in 1655. These two giant moons are bigger than Mercury, as you can see here in this size comparison, but their masses are far less because they contain large amounts of water ice rather than iron. If you look closely at Mercury's surface in high-resolution images, you'll see its appearance is similar to that of our moon superficially. It shows extensive mare-like plains formed by ancient lava flows and heavy cratering indicating bombardment by asteroids and comets, indicating that it has been geologically inactive for billions of years with no recent volcanic activity or plate tectonics. But it obviously was geologically active at one point in its history, during its first billion years, because one of the distinctive features of Mercury's surface is the presence of many narrow ridges extending up to several hundred kilometers in length called lobate scarps. We'll talk more about these fascinating features later and what they tell us about Mercury's evolution. One of the most distinctive things you'll notice about Mercury when looking at a globe of the planet is this huge crater on its surface called Caloris Basin, with a diameter of 5,450 kilometers, one of the largest impact structures in the solar system. The impact that created Caloris Basin was so powerful it caused lava eruptions on the opposite side of the planet through seismic focusing and left a concentric ring over 2 kilometers tall surrounding the impact crater, creating one of the most dramatic features on any planetary surface. At the antipode of Caloris Basin, directly opposite on the other side of Mercury, is a large region of unusually hilly terrain known as the Weird Terrain that was formed by seismic waves from the Caloris impact. If you compare this chaotic region to the rest of Mercury's surface, you can see why it would have this descriptive name given by scientists. The terrain consists of blocks and hills that look like the surface was shattered and jumbled by enormous forces. So what's it like on the surface of Mercury if we could somehow stand there protected from the extreme conditions? Well, to start with, the surface temperature is hugely different all over the planet, creating one of the most extreme thermal environments in the solar system. It can range from minus 173 degrees Celsius in permanently shadowed craters at the poles to over 427 degrees Celsius on the equator at noon, when the sun is directly overhead. It never rises above minus 93 degrees at the poles though, because there's no atmosphere retaining the heat that falls on sun-facing slopes, so the coldest permanently shadowed regions remain incredibly cold despite Mercury's proximity to the sun. This means that there's quite a big difference between the equator and the poles, spanning 600 degrees Celsius, one of the largest temperature ranges in the solar system. But this extreme variation is also due to its orbit and rotation, which we will get back to later when we discuss Mercury's unusual 3.2 spin-orbit resonance. The subsolar point where the sun is directly overhead reaches about 427 degrees Celsius, while on the dark side of the planet the temperatures are on average minus 173 degrees, a dramatic shift happening across the terminator line. Because Mercury is too small and hot for its gravity to retain any significant atmosphere over long periods of time, with an escape velocity of only 4.3 kilometers per second, it's not able to retain any of the heat it gets from being so close to the sun through atmospheric insulation, which is why the dark side of the planet is so much colder than the side facing the sun despite being on the same small world. Mercury, however, does have an exosphere, which is like an extremely thin atmospheric-like volume surrounding the planet that barely qualifies as an atmosphere. Molecules in an exosphere are gravitationally bound to a planet, orbiting ballistically like tiny satellites, but the density is so low at about 10^4 particles per cubic centimetre that it can't behave like a gas because the molecules don't collide with each other as they would in a true atmosphere. In this picture taken by Messenger, you can see the Messenger probe's view of Mercury's exosphere visualised using special filters. When solar wind hits the planet, it rips off certain atoms out of the exosphere through a combination of processes. And what's left is this trail of atoms going into space, creating the sodium tail we discussed earlier. We call this stream of particles the planet's tail, and every planet has this to a certain extent, including Earth, though Earth's is much less pronounced. Earth even does have an exosphere, but it starts at about 600 kilometres above the surface, where the atmosphere becomes so thin that atoms can travel hundreds of kilometres without colliding with each other. It's really the point where space and the atmosphere meet in a gradual transition. Now, in the case of Mercury, this exosphere is not at all stable over time. Atoms are continuously lost and replenished from a variety of sources which we'll discuss in more detail later, including solar wind sputtering, micrometeorite impacts, and photon-stimulated desorption, where solar radiation directly kicks atoms off the surface. NASA has been able to confirm through messenger observations that craters at the North Pole of Mercury contain water ice deposits, perhaps billions of tons of it. Mercury also has something which Mars lacks despite Mars being larger, an actual magnetosphere or a magnetic field all around the planet generated internally. It is only about 1.1% as strong as Earth's magnetic field, far weaker than our planet's protective shield, but it's still strong enough to deflect a lot of the solar wind around the planet and create a miniature magnetosphere that protects the surface from some of the worst solar radiation. Mercury has the most eccentric orbit of all the planets in our solar system, with an eccentricity of 0.206, meaning its orbit is noticeably elliptical rather than circular, with a distance from the Sun ranging from 46 million kilometres at perihelion to 70 million kilometres at aphelion, a variation of more than 50%. Now, this is something a bit hard to imagine without visualization, but bear with me as I explain Mercury's unusual rotation. Mercury takes about 88 Earth days to complete an orbit around the Sun, making it the fastest orbiting planet. It also has a 3.2 spin-orbit resonance of the planet's rotation around its axis, a unique configuration in our solar system. This means it spins 3 times around its axis for every 2 times that it orbits around the Sun, locked in this mathematical relationship by tidal forces from the Sun. It takes about 59 Earth days for Mercury to rotate on its axis once, which is what we call a sidereal day measuring rotation relative to the stars. By pure coincidence, this is almost exactly half its synodic period in respect to Earth, which is 116 days measuring the time between similar configurations of Earth and Mercury. So between conjunctions of Earth and Mercury when the planets align, Mercury rotates on its axis exactly twice. Historically, there was a big problem with that coincidence that delayed our understanding of Mercury's true rotation. Because of this coincidence, we believed that Mercury was tidally locked to the Sun for the longest time, showing the same face to the Sun always, just as the Moon shows the same face to Earth. You see, Mercury orbits closely around the Sun, at an average distance of only 58 million kilometres, meaning it was always tricky for astronomers to get a good look at it for most of its year because it appears close to the Sun in our sky. When it finally got in a good viewing angle from our perspective during greatest elongation, we'd have a look at the face of the planet through telescopes. 116 days later, we'd have another look during this prime observation alignment and see the same face again through our telescopes. So, to astronomers in the 19th and early 20th centuries, it showed that Mercury was tidally locked to the Sun like they expected based on theoretical calculations. What astronomers didn't realise is that Mercury had rotated exactly twice on its axis during this time interval, completing 2 rotations while appearing to show the same face due to the geometric alignment. It wasn't until radar observations of the planet in 1965 by Gordon Pettengill and Rolf Dice using the Arecibo radio telescope that we found out that it does rotate slightly faster than it orbits, completing 3 rotations for every 2 orbits. This 3-2 orbital resonance means that if you were actually standing on Mercury at a fixed location, it would appear that one day from sunrise to sunrise, or what is called a solar day measuring the Sun's apparent motion, is 2 Mercurian years or 176 Earth days. Standing on Mercury observing the Sun, that would look something like this in a time-lapse animation. You would see the sun rise relatively fast from the eastern horizon, and then as it approaches midday climbing toward the zenith, it slows down and even starts going backwards in an apparent retrograde motion, before continuing on again to sunset in the west. As you can see in the animation, that took a whole Mercurian year of 88 Earth days, which means a nighttime on Mercury also takes a year, creating the longest day-night cycle of any planet in the solar system. The sun starts going backwards in the sky at certain locations because approximately 4 Earth days before perihelion, when Mercury is closest to the sun, the speed in which Mercury travels along its orbit equals the speed in which it's rotating on its axis. At this point, the sun's apparent motion across the sky stays stationary, creating a phenomenon visible from certain locations on Mercury. At perihelion itself, when Mercury is moving fastest, Mercury's orbital speed exceeds its rotational speed by a significant margin. So to a person actually standing on Mercury at certain longitudes, the sun appears to move backwards across the sky for several Earth days, a bizarre sight unlike anything experienced on Earth. 4 days after perihelion, as Mercury begins to slow down in its orbit, the sun's normal eastward motion resumes and continues until sunset. You can see this even clearer from a top-down perspective of Mercury orbiting the sun. Twice during Mercury's orbit, from the perspective of certain locations on one of its hemispheres, the sun seems to pause in the sky and then continue on again, creating what astronomers call hot poles. Something else to notice about Mercury's orbit is that it's inclined by 7 degrees to the plane of Earth's orbit called the ecliptic. As a result of this significant inclination, we can only see Mercury transit in front of the Sun when it's directly between us on Earth and the Sun itself at inferior conjunction. And because its orbit is inclined by 7 degrees to the ecliptic, this only happens about once every 7 Earth years on average, when Mercury crosses the ecliptic plane exactly at conjunction, creating transits that were historically important for measuring the Sun's distance from Earth. The last thing we'll discuss about the rotation of Mercury is that its axial tilt is almost zero, with the best measured value as low as 0.027 degrees, essentially perpendicular to its orbital plane. This is even smaller than that of Jupiter, which has been measured at 3.1 degrees, making Mercury the planet with the smallest axial tilt in the solar system, and meaning it has no seasons caused by axial tilt, unlike Earth's 23.5 degree tilt that creates our dramatic seasonal variations. And finally, do you want to see Earth from Mercury in a way that provides cosmic perspective? Well, here we are, just a couple of pixels across in this image taken by Messenger. This photo was taken from the Messenger probe several years ago from a distance of tens of millions of kilometers, and barring the newborn since the photo was taken, every single one of us was in this picture when it was captured, all of humanity compressed into those few bright pixels. But what was Messenger, and why was it so important to our understanding of Mercury? Well, let's start with a little context about the history of Mercury exploration. When mankind first started sending spacecraft out to explore the solar system in the 1960s, the first planet to be visited was Venus, our closest neighbour, in 1962 with NASA's Mariner 2 spacecraft. Next was Mars in 1965, with Mariner 4 providing our first close-up images of another planet, and then Jupiter in 1973 with Pioneer 10 beginning the exploration of the outer solar system. Only then came Mercury in 1974 with Mariner 10, despite being closer to Earth than any of those other worlds. And already this order might seem a little odd when you think about it logically. The closest distance between Earth and Mercury is 77 million kilometers, closer than any other planet on average. In fact, it is the closest planet to us on average due to its orbital mechanics, spending more time near Earth than Venus does. The closest distance between Earth and Jupiter is 588 million kilometers, almost 8 times that distance to Mercury. And Jupiter was visited again in 1974 with Pioneer 11, twice in 1979 with Voyager 1 and 2, providing stunning close-ups. In 1992 when Ulysses flew by, in 1995 when Galileo entered orbit, in 2000 when Cassini passed through on its way to Saturn, and in 2007 when New Horizons used Jupiter for a gravity assist. Multiple missions were launched to Saturn, including Voyager and Cassini, to Uranus and Neptune with the Voyagers, to comets like Halley and asteroids like Eros, while Mercury got nothing for 30 years after Mariner 10. Is this because it was deemed uninteresting by mission planners or because it had been thoroughly explored? Did we discover everything there was to discover about it with that single first mission that mapped less than half the surface? No, not at all. The first mission was a flyby series that only mapped about 40 to 45% of Mercury's surface in black and white images, with limited resolution. Actually, the real reason for the neglect is that Mercury is one of the most challenging planets to visit in our entire solar system from an orbital mechanics and engineering perspective. Why is it so difficult when it's so close? Well, as previously mentioned, Mercury exists in a furnace created by the Sun's proximity. Due to its proximity to the Sun receiving 10 times the solar radiation Earth does, its surface temperature reaches highs of 430 degrees Celsius, hot enough to melt lead, tin, and zinc. So any probe visiting it would need to be highly heat-resistant with special thermal protection systems, including heat shields and radiators. But that same proximity to the Sun means that any probe launched towards Mercury will accelerate faster and faster due to the immense gravitational pull from our star that increases as the inverse square of distance. Using rocket fuel to counteract that acceleration would be like swimming up white water rapids, fighting against a current that grows stronger the closer you get. Combating the Sun's gravity required too much fuel for a Discovery-class spacecraft to carry within mass and volume constraints. Slowing down the spacecraft enough to be caught up in Mercury's weak orbit seemed impossible with conventional propulsion systems. It was a question of weight and the rocket equation. Weight is a challenging limitation when it comes to spacecraft design and launch costs. The heavier a craft, the larger a rocket needed to get it out of Earth's orbit, and the more expensive everything becomes following an exponential cost curve. Scientists try to keep everything as light as possible to reduce this cost, sometimes making painful choices about which instruments to include. As fuel takes up precious weight allocations that could go towards scientific instruments or more capable communication systems, scientists try to only take what is necessary to help them complete their journey to the target. However, for about 30 years from the mid-1970s to the mid-2000s, scientists could think of no way to put enough fuel on a probe to get it to slow down enough to enter Mercury's orbit, using conventional chemical propulsion, especially if they wanted scientific equipment on board too that would make the mission worthwhile. So after the success of Mariner 10's flyby missions of Mercury in 1974 to 1975 that provided tantalizing glimpses of this world, Mercury exploration was put on hold while mission planners searched for solutions. But in 1985, an orbital mechanics expert named Chen-Wan Yen, working at NASA's Jet Propulsion Laboratory, realized that there was a way of getting a probe into orbit around Mercury that didn't need new technology or massive amounts of fuel. Instead, she had worked out a particular route an orbiter could take around the solar system that would slow it down enough to enter Mercury's orbit with only a few course corrections using chemical thrusters, revolutionizing our approach to Mercury missions. Rather than going straight to Mercury on a minimum energy transfer orbit, the orbiter would need to go a much longer way through the inner solar system. How long and complex was this trajectory? Under Chen-Wan Yen's model, a craft would orbit the Sun about 15 times over 6.5 years, flying past the Earth once, Venus twice, and Mercury 3 times before finally slowing down enough to enter its orbit on the 4th Mercury pass. All these planetary flybys would be essential for velocity reduction. By skimming through the planet's gravitational fields at precisely calculated altitudes, vital speed could be shaved off from gravity assists that bend the trajectory and reduce velocity, and from atmospheric drag in Venus's case, all due to the gravitational interactions with the planets that transfer momentum. The entire route would cover a mammoth 7.9 billion kilometers, more than the distance from the Sun to Pluto, and would take 6.5 years to complete. Chen-Wan Yen's findings were not immediately picked up by NASA mission planners focused on other priorities. But in 1998, NASA began to take an interest in the idea as part of their Discovery program for small, focused planetary missions, and after seeing the feasibility of the route through detailed computer simulations, they launched the Messenger probe in 2004 from Cape Canaveral. Messenger, or the Mercury surface, space environment, geochemistry, and ranging probe was only about 1.85 meters long and 1.3 meters wide and weighed 100 kilograms at launch, including fuel. This is small and light for a typical NASA planetary mission. Just as a comparison, Juno spacecraft that orbits Jupiter is 20 meters long from solar panel tip to tip, nearly 10 times larger. Messenger came equipped with a powerful thruster system, a ceramic fabric composite heat shield to protect it from the sun's intense radiation, reaching 11 solar constants, 2 solar panels with special reflective coatings, and louvers to manage heat, and a whole suite of scientific equipment for imaging and measuring data from Mercury, including cameras, spectrometers, magnetometers, and a laser altimeter. Scientists hoped to take advantage of this opportunity to learn as much as they could about Mercury, including the chemical composition of Mercury's surface through X-ray and gamma-ray spectroscopy, its geological history by mapping the entire surface, its magnetic field using sensitive magnetometers, and its core structure through radio tracking and gravity measurements, among other things. Messenger spent its first year in space making one orbit around the Sun before meeting back up again with Earth in August 2005. This gave scientists a chance to test its equipment on a known astronomical body to make sure there weren't any errors or calibration issues and to make any adjustments as needed before the spacecraft ventured too far away. Messenger took some photos of Earth and the Moon from unique perspectives showing our planet as a crescent, and also tested its other equipment to take readings of our atmosphere and magnetosphere. Fortunately, everything was working perfectly after a year in the harsh space environment. As it began to head further sunward toward the inner solar system, Messenger employed a clever technique to help reduce its acceleration towards the Sun beyond just using planetary gravity assists. It used its solar panels to catch solar radiation, like sails on a ship might catch wind, orienting them at angles to create a small but continuous braking force. Solar radiation hitting an object actually pushes it very slightly through momentum transfer from photons. While this force is very tiny, measured in micronewtons because Messenger's journey was so long spanning years, it really added up to significant velocity changes. Making the most of this phenomenon through careful attitude control was one of the ways Messenger saved propellant and decelerated naturally without burning precious fuel. The next notable landmark in Messenger's journey came in 2006, when it did its first flyby of Venus on October 24th. Sadly for scientists, this moment came at a time when Venus was exactly on the opposite side of the Sun from Earth, which meant Messenger was not in radio contact due to solar conjunction. It did take some photos of the planet which it later sent back when contact was re-established, but otherwise it performed no science during this flyby since data couldn't be transmitted. However, in 2007, on June 5th, it passed Venus again at a closer distance. At that time, another spacecraft was orbiting Venus, ESA's Venus Express that had arrived in 2006. Messenger and the Venus Express took the opportunity to work together, performing the first ever simultaneous measurements of particle and field characteristics of the planet from 2 different locations, providing a 3-dimensional picture of Venus's magnetosphere and how it interacts with the solar wind. But then it was on to the main event after years of preparation, Mercury itself. Messenger made its first flyby of Mercury on the 14th of January 2008 with everything going smoothly and all instruments functioning perfectly. The spacecraft passed just 200 kilometers above the surface, capturing over 1,200 images. The same successful operation was true of the second flyby on October 6, 2008, which provided complementary coverage of different regions. But during the third flyby in September 2009, something went wrong that could have ended the mission. Messenger went into safe mode, an automatic protective state designed to protect systems on the craft in the event of an error or anomaly. How disappointing and stressful it must have been to have come so far over 5 years, only for the mission to potentially fail during one of the final stages before orbital insertion. Messenger remained in safe mode for what must have been 7 hours of extreme stress for all the scientists involved at mission control. You see, Messenger had to pass through Mercury's shadow during this flyby, meaning it would lose solar power and had to rely on its batteries for 18 minutes while in darkness. Something wasn't configured right in the power management part of the software that controlled the transition between solar and battery power. Fortunately, Messenger's computer detected the error and reset once power from the panels charged the battery back up after exiting Mercury's shadow, and it was able to continue with its mission programming, swinging around the Sun one more time before finally entering orbit around Mercury on the 18th of March, 2011, becoming the first spacecraft ever to orbit Mercury. Messenger took up an elliptical orbit around Mercury with a 12-hour period, alternating between as close as 200 kilometers at periapsis and as far away as 15,000 kilometers at apoapsis over Mercury's north pole. This highly elliptical orbit was chosen carefully for specific reasons. Mercury acts sort of like a giant sun mirror radiating heat back into space from its sun-baked surface. Remaining too close to Mercury for extended periods was too hot for Messenger, even with its sophisticated heat shield, which was more designed to protect it from direct solar radiation 7 to 11 times more intense than at Earth, rather than thermal emission from the planet itself. So moving further away every 12 hours in its orbit gave the spacecraft a chance to cool off by radiating heat to space from its sunshade, preventing the instruments from overheating and maintaining operational temperatures. Messenger spent the next 4 years in Mercury's orbit studying the planet intensively, far exceeding scientists' hopes and expectations for the mission duration, as they had originally planned for it to only last 1 Earth year initially. Before launch, scientists had hoped that Messenger would take at least 1,000 photos over the course of its lifetime to map the previously unseen portions of Mercury. However, Messenger exceeded all expectations and took over 250,000 photographs during its extended mission, giving us a complete map of Mercury's surface in high resolution and colour, with multiple wavelengths revealing composition, as well as photographing nearby comets passing through the inner solar system and taking calibration images of other planets and stars. The mission revolutionized our understanding of Mercury in virtually every way. On the 25th of December 2014, Messenger's propellant supply, so carefully saved and managed over 10 years in space, was finally about to run out after years of orbit corrections. By this point, Mercury's gravity had pulled Messenger into an even lower orbit, with the spacecraft orbiting a mere 25 kilometers from the surface of the planet at its closest approach, providing unprecedented resolution, but making the spacecraft vulnerable to crashing. Scientists gave the thrusters one last burst to extend its orbit and mission, lifetime for as long as possible, squeezing out every last bit of science. But on the 30th of April 2015, Messenger crashed into the surface of Mercury at several kilometers per second after exhausting all its fuel. After a journey that had lasted over a decade and had covered literally billions of kilometers through the inner solar system, Messenger's incredible journey had come to an end, creating a new crater about 16 meters wide on Mercury's surface as a permanent memorial to this historic mission. Messenger gave us a wealth of insights into Mercury before it died that revolutionized planetary science. Onboard Messenger were a host of scientific instruments totaling 11 major systems, including a magnetometer to map out Mercury's magnetic field in 3 dimensions, which is thought to be generated by a dynamo effect in its molten outer core similar to Earth's magnetic field generation. Our planet's fast rotation and tidal stretching from our moon keeps our outer core in vigorous convection, generating Earth's strong magnetic field. But Mercury doesn't have a moon to provide tidal heating or a fast rotation since it takes 59 days to spin once. What it does have, however, is an eccentric orbit more so than any other planet with an eccentricity of 0.206. The Sun's gravitational strength increases and decreases significantly, as Mercury gets closer and further away from the Sun during each orbit by more than 50%. So, the tidal forces from the Sun pull and squeeze on the planet's interior in a varying pattern, the friction of which keeps Mercury's outer core molten and convecting, maintaining the dynamo that generates the magnetic field. Unlike Earth's magnetic field, which is roughly centered in the planet, Mercury's field is offset from the center by about 20% of the planet's radius toward the north, creating an asymmetric magnetosphere. And we don't really know why this offset exists, though it may be related to the structure of the core or mantle. Its magnetic field is only about 1% as strong as Earth's at the surface, but this still has an important impact on deflecting a significant portion of the solar wind around the planet and creating a protective magnetosphere. However, due to Mercury being closer to the Sun, the solar wind pressure is a lot greater here than it is around Earth by about a factor of 10 at perihelion. Add a weak magnetic field to the mix, and the magnetosphere around Mercury is compressed very closely to the planet's surface, extending only about 1 Mercury radius above the surface. Earth's magnetosphere, on the other hand, extends many times the diameter of the planet away from the surface on the day side, and stretches into a long magnetotail on the night side. Interestingly, these factors make the magnetosphere of Mercury highly dynamic and variable. What does that entail for the physics occurring there? Well, for one, reconnection events are 100 times more common around Mercury than around Earth. occurring every few minutes rather than every few hours. Reconnection events occur when magnetic field lines snap together and reconnect in different configurations as the charged solar wind pushes against the planet's magnetosphere with varying pressure. When this happens, it allows some of these charged particles to break into the planet's magnetosphere through the reconnection point, entering a region of plasma in the planet's magnetotail behind the planet. The flows you see in this scientific simulation of Mercury's magnetosphere in the plasma region are from reconnection events that inject solar wind plasma into what would otherwise be a relatively empty region. Another fascinating feature of the magnetosphere that MESSENGER detected was energetic bursts of electrons producing hundreds of thousands of electron volts of energy, far more than expected. As MESSENGER orbited Mercury over 4 years, it picked up thousands of these events during close approaches, and mysteriously they were mainly localized in the northern hemisphere and were compressed towards the planet along the sun-facing side. This is still an ongoing field of study with scientists working to understand the acceleration mechanism. However, scientists believe these electrons have been accelerated through magnetic reconnection and other processes in the magnetotail, and they follow the direction of the magnetic field lines around from the South Pole to the north, explaining the hemispheric asymmetry. MESSENGER also hosted a wide array of spectrometers to study composition. Spectrometers are important instruments for detecting the composition of mineral deposits on the surface, without actually having to take a physical sample and return it to Earth for analysis. Spectrometers can also be used to detect the particles in the atmosphere or exosphere. Now, Mercury doesn't have an atmosphere per se in the traditional sense, but as previously mentioned, it has an exosphere or an extremely tenuous atmosphere with surface pressures of about 10 Junzerl 15 bar. It is so thin that the particles within it don't interact with each other as gas molecules normally do. But what MESSENGER found out about this exosphere's relationship to the surface really surprised scientists and overturned previous theories. Mercury is covered with volatile substances that should have been lost during its formation. It isn't just a fried rocky planet stripped of volatiles by its proximity to the Sun, as scientists expected. It seems to be covered in potassium, magnesium, sulfur, sodium, calcium and chlorine at a higher level than any other terrestrial planet and much higher than on our Moon, which formed in the outer regions of Earth's protoplanetary disk. The fact that its volatile ratios have more in common with Mars than with Earth and Venus have completely disproved a lot of solar system formation theories that existed before MESSENGER arrived at Mercury, requiring new models of how the inner solar system formed. These volatiles are constantly being blasted off by radiation from the Sun through various processes, more so at the equator than near the poles due to higher temperatures and more intense solar radiation at lower latitudes. This may explain why on the surface some substances like potassium are more abundant in the northern hemisphere and near the poles than around the equator. It is much hotter on Mercury around the equator where noon temperatures exceed 400 degrees Celsius than at the poles where temperatures in permanently shadowed craters never rise above minus 170 degrees, so the potassium there at low latitudes would have been heated enough through solar radiation that much of it has been lost from the surface to the exosphere and eventually to space over billions of years. Now, the exosphere contains a lot of the particles you would also find on the surface like sodium, potassium, calcium, magnesium, and the others I mentioned earlier. This exosphere is not at all stable as we discussed. Solar wind picks up and carries away a lot of charged particles through sputtering and plasma processes. And solar light pressure also pushes a lot of the neutral particles away from the planet through radiation pressure acceleration. Were it not for the processes that continuously replenish the exosphere from the surface, Mercury would lose it all to space over a relatively short time frame of perhaps a few months. While most substances in the exosphere certainly do come from the planet's surface through impact vaporization and other processes, it also contains other elements like hydrogen and helium which cannot be found in significant quantities in Mercury's rocky surface. So where did they come from if not from the planet itself? Well, as you may know, the Sun is made predominantly of hydrogen and helium, about 73% and 25% by mass respectively. And interestingly, the solar wind that streams from the Sun carries these particles to Mercury in a constant flow. Some of the solar wind particles actually get caught up in the exosphere temporarily through a process called charge exchange and stays for a while before being ionized and swept away. As far as we know, this capture of solar wind is the only major source of hydrogen and helium in Mercury's exosphere, providing direct sampling of solar material. In these false colour images created by MESSENGER, we see calcium being emitted from the exosphere. An unknown process or combination of processes means it's much more prevalent in the exosphere during the planet's dawn side than dusk side, creating an asymmetric distribution, and magnesium streaming away from the night side of the planet in a tail structure. In fact, Mercury's sodium tail has been known about for a while, since 2001, as we discussed. In these dramatic images processed to enhance the tail, sodium ions are lit up as they stream away from the planet at the characteristic 589 nanometer wavelength, making Mercury look like a comet with its glowing tail. Incredibly, if you were to look up into the night sky on Mercury with specialized sodium filters, you would actually see a faint yellow glow reminiscent of city lights on Earth or aurora, though the mechanism is completely different. This tail is seasonal, as we explained earlier. The eccentric orbit of Mercury means that its distance to the Sun varies throughout its year from 46 to 70 million kilometers, and as it orbits, its orbital speed also changes according to Kepler's second law. So, the time of greatest sodium emission and tail visibility is actually when Mercury is travelling away from the Sun at maximum radial velocity about 16 days after perihelion, due to the Doppler shift effect we discussed that makes solar radiation at 589 nanometers available. There was one other curious substance found in Mercury's exosphere that scientists really weren't expecting to find. Water vapour in small amounts but detectable quantities. This could come from cometary tails as they pass by Mercury, depositing water molecules, or it could come from the ice deposits MESSENGER detected around the planet's poles sublimating from crater walls. Surprisingly, water ice can exist on this scorched planet that seems like the last place you'd expect to find frozen water, but only at the bottom of permanently shadowed craters near the poles, forever protected from directly interacting with the sun's light rays that would cause immediate sublimation. The Earth-based Arecibo radio telescope had already detected highly reflective regions around the poles before MESSENGER's arrival using radar observations in the 1980s, and as images from MESSENGER came in during its orbital mission, these radar-bright regions matched up perfectly with regions of permanent shadow at the bottom of large craters, providing strong confirmation. Estimates put the amount of water ice found on Mercury at somewhere between 100 billion and 1 trillion kilograms, a substantial amount. This isn't huge by Earth standards, where our oceans contain over 10 to 21 kilograms, but it would be a significant resource to any future human colony there if we ever develop the technology to establish a presence on Mercury, providing water for life support and potentially rocket fuel through electrolysis. There were some other surprising features found on Mercury's surface too, beyond just craters and volcanic plains. Hollows were found dispersed all over the surface in hundreds of locations. These are a unique feature to Mercury not seen on any other planet or moon. While we aren't completely sure what causes them, they may be formed by volatile substances sublimating directly from solid to gas when exposed to solar radiation and creating the depression, and they are unique to Mercury simply due to the combination of Mercury's composition and proximity to the Sun. They seem to be an active ongoing geological process based on their fresh appearance, apparently some of the youngest features on the planet forming perhaps within the last few million years, and they are certainly not the result of meteor impacts based on their morphology and distribution patterns. There is much more going on Mercury's surface than anyone expected. Ancient dried-up lava flows covering vast areas of the surface, evidence of extensive volcanic activity, particularly between 3.7 and 4 billion years ago. Craters from massive asteroid strikes that warmed its surface and created basin structures that fundamentally shaped the planet's geology. And surprisingly, the thin Labatt scarps that were evidence of its gradual cooling and contraction over billions of years. These scarps show that Mercury is shrinking as its interior cools, and from MESSENGER's precise topographic data using laser altimetry, Mercury has contracted by over 14 kilometers in diameter since its formation about 4.5 billion years ago, a lot more than was expected from thermal models, and suggesting either a hotter initial state or different cooling history than predicted. All these findings have thrilled scientists working on planetary evolution. Yet, even though we would barely know anything about Mercury, were it not for MESSENGER's 4 years of intensive study, somehow this mission isn't that well known among the general public compared to missions like Curiosity rover or Cassini. Perhaps ESA's Bepicolombo mission, already on its way to Mercury right now, having launched in 2018, will better capture the public's imagination when it arrives in December 2025 and begins its comprehensive two-spacecraft study of Mercury. Let's go back billions of years to when the planet was much warmer than it is today. So warm, in fact, that it becomes necessary to ask an important and fascinating question about planetary evolution. What happens when a planet melts, when temperatures rise so high that the very rocks that make up a world begin to flow like liquid? For Mercury, this is no idle question or theoretical exercise. At the risk of it being understated given the extreme nature of the conditions, Mercury is a very hot planet even today. With daytime temperatures reaching an incredible 427 degrees Celsius, approaching the temperature of some wood-burning fires, and hot enough to melt lead, zinc and tin, the rocks and dust on Mercury's surface bake beneath a blistering heat that pushes them towards their melting points. It's not the hottest planet in the solar system despite being closest to the Sun. That honour goes to Venus thanks to its thick carbon dioxide atmosphere creating a runaway greenhouse effect that traps heat and raises surface temperatures to 465 degrees Celsius. But Mercury is certainly up there in second place for surface temperatures. The Mercury we know today has actually cooled considerably over the billions of years since its formation, when it was a molten ball of rock and metal. There is water ice at its polar caps in permanently shadowed craters as we discussed, and we discussed the signs on its surface like lobat scarps that show it has contracted over time as its interior became colder and the planet shrank. So what was it like back then 4 billion years ago? When rock is sufficiently heated beyond a critical temperature, its solid crystalline structure breaks down and it turns into the gloopy viscous liquid known as magma or lava once it reaches the surface with a viscosity or runniness about 10,000 or 100,000 times more viscous than water depending on composition. For a point of reference, this is similar viscosity to honey or tomato ketchup at room temperature, although I would definitely not recommend putting molten rock on your food, as it would vaporize it instantly. Depending on the rock type and composition, magma forms at temperatures of at least 600 degrees Celsius for some silicate melts, but potentially as high as 300 degrees Celsius, or more for other compositions like basaltic magma that is common on terrestrial planets. So, for Mercury to have begun to melt during its early history, we know that it must have reached at least these temperatures throughout large portions of its interior to generate the extensive lava flows we observe today. In spite of lava being much less runny than water by many orders of magnitude, lava can still travel for great distances before stopping and solidifying. This is because once the surface of a lava flow hardens through cooling and solidification, it forms an insulating layer that keeps the rest of the lava within protected from radiative heat loss, so it can flow freely underneath for kilometers. How do we know this volcanic activity happened on Mercury, and that the planet once had a molten surface layer? The clues can be found in craters like Radit Ladi, which tell the story of Mercury's volcanic past. Scientists estimate that Radit Ladi is a relatively young crater, likely under 1 billion years old based on crater counting statistics, with well-preserved walls and a floor relatively clear of other later impacts that would have degraded its structure. It's large at over 250 kilometers in diameter, big enough to be visible from Earth in large telescopes. Notice how rough the hills and ejecta deposits are around the crater rim, and yet inside is a remarkably smooth plain with few large features. This dramatic difference is no coincidence, but tells a story of volcanic processes. Originally, the terrain inside Radit Ladi was likely about as rugged as the hills around it, created by the impact excavation and ejecta. So why is it so smooth now millions of years later? The answer is lava flooding after the impact. When lava is left on its own without external forces, it will try to form the flattest surface possible, just like water does if you put it in a bowl, as it is dragged down under the effects of gravity seeking the lowest potential energy state. The same physical principle happened here at Radit Ladi. An asteroid crashed into the planet's surface, creating a deep basin, and the crater quickly filled with lava either from the impact itself or from subsequent volcanic activity. Once the lava cooled over perhaps thousands of years, it formed the smooth plain you see here today. But where did this lava come from that flooded Radit Ladi and hundreds of other craters on Mercury? There are two theories that scientists debate. The first is that the impact of the meteor triggered a volcanic eruption, as magma from beneath the surface found pathways through the fractured crust and rose up through the cracks to fill the basin, driven by buoyancy and pressure from below. The second explanation is that the surface within the crater got so hot due to the impact of the meteor releasing kinetic energy that it pushed the already hot rock crust over the tipping point into melting, creating what's called impact melt. This kind of lava is known as impact melt and is common in large craters throughout the solar system. The true explanation is likely a combination of both processes working together, with impact melt providing initial flooding and volcanic activity, adding additional material over millions of years. Now that we know that smoothness in crater interiors is a sign of lava flow, we suddenly realize that there are numerous other craters on Mercury that similarly must have been filled with lava during Mercury's volcanically active period. Just look at Rustaveli, where crags of mountain can be seen poking up through the smooth lava layer like islands in a frozen sea, or Copland Crater with its distinctive smooth floor, or Polygnotus with its complex interior structure, or Rachmaninoff, which is particularly fascinating. Rachmaninoff is particularly interesting, as here you can see the strong indicators of lava bubbling up through, from beneath the surface to the centre of the crater, in a classic volcanic pattern. Take a look at the strange crinkled cracks, forming a rough circle inside the central crater floor. Such features called floor-fractured craters are a signal that a slower outpouring of magma pushed up from beneath the surface over an extended period, breaking the solidified plane, then pushing up through the cracks and then cooling again under the effects of Mercury's fluctuating temperature between day and night. Here and in many of these impact craters scattered across Mercury's surface, the collisions from space triggered deep volcanic activity from within Mercury's mantle, tapping into reservoirs of molten rock that were waiting to escape. But lava didn't just flow within the circular confines of craters. Let's look at the valley known as Ancor Vallis in Mercury's northern hemisphere. Here you can see clear signs of smooth lava flow covering hundreds of square kilometres, but this time moving like a river downhill following gravity. The lava travelled from high to low ground, following the topography until it eventually poured into the basin next to it, creating channels and levees that record the direction of flow. Flows like these ended up filling massive seas or maria, taking up vast swaths of the planet and turning them the more orangey colour we see today in enhanced colour images. Scientists have begun to recognise this telltale orange or tan colour in enhanced imaging as a sure sign of volcanic plains formed by basaltic lava flows, and from it, a more detailed picture has begun to emerge of conditions on early Mercury that make it even less hospitable than we imagined. Areas like this one to the northeast of Rachmaninoff crater are likely formed by explosive volcanic activity rather than effusive lava flows. When Messenger flew over this area in 2015 during one of its low-altitude passes, it took detailed photos of it and found the surface to be covered in a fine dust layer unlike the coarser material elsewhere. Upon review and spectroscopic analysis, it was obvious what this dust was to the planetary geologists studying the images. Volcanic ash that must have fired out of volcanic vents explosively and covered the terrain around it in a blanket of pyroclastic material. NASA scientists likened it to snow falling from the sky, but of course much different in composition and temperature. Fiery, hot, angry snow made of silicate particles and glass shards ejected at high velocity. So, it wasn't just lava flowing beneath your feet that you'd have to contend with on early Mercury, but burning ash falling from the sky at hundreds of degrees Celsius, choking the tenuous exosphere and coating everything in a layer of volcanic debris. And that was just the calmer volcanic eruptions. The final indicator of volcanic activity on Mercury hints at eruptions so destructive and violent that whole chunks of the crust were scooped out of the planet in explosive events. Take a look at this crater called Navoi in Mercury's southern hemisphere. This is no ordinary impact crater despite its circular shape. When an impact crater is formed onto a hard surface, one that's not sufficiently hot to melt into lava immediately, a central peak is usually formed through a well-understood process. This is because when the crater walls suddenly find themselves exposed after the impact excavation, gravity suddenly exerts itself on all that loose particulate material, which rushes down the walls of the newly scooped-out basin towards the centre following the steepest gradient. Once there, having built up considerable momentum during the descent, it comes crashing into all the rocks and landslide material that is sliding down from the other side of the crater in a violent collision. The two sides meet in the middle, and all that momentum and kinetic energy forces them to keep moving in the only direction they can, upward. You see the same effect more clearly when you throw a large rock into water, creating a splash. The water of the newly formed basin rushes in to fill the gap, but then crashes into water from the other side, moving in the opposite direction. And all of it shoots upward in a powerful secondary splash before gravity pulls it back down. But unlike water, which quickly levels out, the sand and loose rock of an impact crater does not level out completely, but forms a central peak that remains as a permanent feature. Depending on what angle the meteor impacted from, this peak is either perfectly rounded if the impact was vertical, or possibly teardrop-shaped, or offset if the impact came in at an angle. However, the rays and central formation of Navoi crater are neither of these things you'd expect from an impact. As scientists looked at the morphology of this feature in detail, they came to the conclusion that this crater was not formed by an impact from space at all, despite its circular shape. Instead, it had been carved out through the explosive force of an erupting volcano in what's called a caldera formation. At 66 kilometers in diameter, larger than many impact craters, the amount of force exploding upwards that would have been necessary to carve out this crater and scatter its remnants for kilometers all around must have been truly massive, releasing energy equivalent to millions of nuclear weapons. So, there you have it. A picture of early Mercury's hellish conditions. Meteors raining from the sky constantly during the late heavy bombardment, tipping the rocks they landed on over the melting point through their kinetic energy. Volcanoes bursting forth across the surface, either filling the landscape slowly with bubbling magma in lakes and fiery rivers flowing downhill, or choking the air with burning ash and pyroclastic flows. Not that there was any breathable air to begin with beyond the thick toxic gases emitted with the eruptions, including sulfur dioxide and other volcanic volatiles. And even the ground you could stand on might at any moment explode under your feet as magma reservoirs reached critical pressure. This is what it was like when a planet was melting billions of years ago, a vision of hell that makes Dante's Inferno seem tame by comparison. Mercury is quiet now, geologically speaking. As near as we can tell from orbital observations and surface imaging, there are no longer any active volcanoes on the planet, with the last major volcanic activity occurring perhaps 3 billion years ago. Although the sun still bakes down on it with intensity 10 times greater than Earth receives, the unbridled fury that raged beneath its surface is now calm and soothed, as the interior cooled over billions of years. Yet, for all those who know how to look and read the geological evidence, the evidence of what once was is still there, locked in the geological record preserved in the craters and plains and volcanic features. It's the scars that tell the story of a violent past, a permanent record written in stone and frozen lava. When something is as incredibly difficult to get to as Mercury is from an orbital mechanics perspective, it is extremely tricky to study in detail with spacecraft. Which is one of the reasons why in all of human history spanning thousands of years of astronomical observations, there have only ever been 2 missions to Mercury that actually visited the planet, with just one more currently on the way. Mariner 10 in 1974 and 1975 making 3 flybys, Messenger in 2011 entering orbit for 4 years, and Bepi Colombo due to arrive in December 2025 with its dual spacecraft. Of these prior 2 missions, only Messenger went into orbit around Mercury for an extended period, and so, it is the only mission to ever give us close-up detailed shots of Mercury's surface from a stable platform allowing repeated observations. And crazily enough, some of the formations we've seen on the surface are still unsolved mysteries even more than a decade after Messenger ended its mission, while other formations give us hints at the raw primal power of the early solar system when planets were still forming and collisions were common. So, let's finish this comprehensive exploration by taking a look at some of those mysteries and formations and see what answers we can find in the geological record. When you look at the surface of Mercury in true colour or enhanced colour images, there are a few features that immediately jump out at you even to an untrained eye. First, its colour variation. Mercury's colour is not actually monochrome as it appears in many black and white images from Mariner 10, and is smattered with speckled greys, creams and beiges with lighter sections and linear features. These darker sections are believed to indicate high levels of graphite or carbon-bearing minerals, the same material used in pencils, possibly delivered by carbonaceous asteroids billions of years ago. And the lighter sections representing different mineralogy, well, we'll get onto them later, and what they tell us about Mercury's composition. Beyond that colour variation, you most likely notice the craters when looking at Mercury. Much like the Moon, Mercury is covered with impact craters as ancient pieces of space debris crash down on the unprotected planet, with a roughly even distribution across the surface. These offer fascinating insights into the planet's violent history spanning billions of years and the bombardment history of the inner solar system. You can get a sense for how old a crater likely is by examining how sharp its crater rims are in high-resolution images. Sharp and crisp rims with well-defined edges are likely a lot more recent geologically, formed perhaps within the last billion years, than the older rougher rims that have had more time to erode down due to the natural processes happening on the planet, including micrometeorite bombardment and thermal cycling. Sometimes asteroids strike within the same place as older collisions, creating overlapping craters of differing ages, such as the craters here in this image, creating complex superimposed structures that allow scientists to determine relative ages by examining which crater formed first. But it is in the difference between these older and younger craters that we get our first fascinating clue about the surface of Mercury and how it changes. It is an active flowing place despite appearing dead. Although there is no real atmosphere to produce the weathering we would imagine on Earth with wind and rain, evidently things on the planet's surface do not remain static on an astronomical timescale but change gradually. As previously mentioned, Mercury is cooling as heat escapes from its interior, and as it does so, its surface bunches together in kilometre-long scarps or cliffs as the planet shrinks. But Mercury's surface is not just crumpling and contracting, it is also smoothing out in certain areas through mass wasting. In this crater shown here, there is clear evidence of slumping having taken place in a dramatic landslide. While about 90 degrees of the crater wall has retained its original shape from the impact, the remaining 270 degrees has slipped further into the crater bottom, breaking away from the rest of the rim under the force of its own weight and Mercury's gravity. Scientists are not entirely sure why this happened to only some of the crater, and not all of it in a symmetric pattern. Is the soil particularly hard in the bottom right corner that retained its shape providing support? Was it something to do with the angle the impact struck at creating asymmetric stress patterns? We don't really know with certainty. And that's one of the things that is so intriguing about Mercury and planetary science in general. There is still so much more to discover despite decades of study. Here's another interesting phenomenon that connects Mercury to the Moon. In my videos about the Moon I've made, I mentioned crater rays or ray systems that extend from certain impacts. These spidery lines that radiate out from certain craters are a prominent part of Mercury's surface as well, with some stretching over 400 kilometers across the surface in linear patterns. Their lighter color compared to the surrounding terrain is a sign that the material kicked up from under Mercury's surface during the impact is less graphite-rich, or at least has a different chemical composition to the sun-exposed surface that has been altered by space weathering over billions of years. But did you know that for a while scientists could not account for how these spidery lines were formed during impacts? When they tested different weights of impactors, consistencies of terrain, and speeds of impact in laboratory experiments, they were unable to recreate these ray patterns in lab conditions no matter what they tried. Whatever combination they tested, the material they kicked up in the experiments would always return back down in a consistent circle, creating a symmetric ejector blanket, not thin spiderweb lines radiating outward. Scientists racked their brains for years trying to understand this mystery, but now it seems that this mystery has been solved through an unexpected discovery. In 2018, a scientist called Tapan Sabharwala was scouring the internet for information on crater rays and discovered that a group of students had managed to recreate the spidery line pattern of crater rays in their own experiments. Sabharwala was excited by this finding, but also confused and intrigued. Why were these students able to manage what other scientists with more sophisticated equipment had not been able to reproduce? Interestingly, he realized that this was an example of scientists being too neat and methodical in their experimental setup. Before performing their tests in lab conditions, Sabharwala and other researchers had always prepped the experiment by carefully smoothing out the sand their test asteroid was impacting into, creating an idealized flat surface for the experiment. The students had not done this preparatory step, leaving the test surface rough and irregular with natural variations. This made sense in hindsight, as it more closely mimics the rough, uneven terrain on the surface of an alien planet that has been bombarded for billions of years. And as it turns out, this was the entire key to understanding how these rays were formed through secondary cratering. Crater rays do not care primarily about the speed of the impact, the angle of approach, or the composition of the crust beneath. They only care about the surface shape and how rough it is at the scale of meters to kilometers. Knowing that this is how these rays are formed through secondary impacts of ejector blocks, it really opens your eyes to the scope of some of the impacts that have struck Mercury in its violent past. Remember I mentioned how some of these ray systems stretch over 400 kilometers from their source crater? That was just the smaller ones that are relatively common. Look at the extensive ray system originating from the crater known as Hokusai in Mercury's northern hemisphere. These rays must have been created from an incredibly powerful impact, as their lines stretch almost entirely around Mercury's surface to the opposite hemisphere, which by the way has a circumference of 15,229 kilometers at the equator. The ejector from this single impact travelled thousands of kilometers before landing and creating secondary craters, and although not quite as large as Hokusai's rays, the ray system of the crater Debussy covers over 1,000 kilometers and is equally impressive in its extent. While the Moon also has prominent ray systems like those from Tycho and Copernicus craters, they are usually smaller than Mercury's largest examples. In fact, one of the main visual distinguishing aspects of Mercury compared to the Moon are these giant ray systems that span entire hemispheres. These show us that one of the formative processes that explain Mercury's unique surface appearance is incredibly powerful bombardments by high-velocity impactors. Seeing as the Sun is so nearby with its immense gravity, objects caught in this intense gravitational pull would crash into Mercury with far more force than Mercury's own weak gravity could produce, accelerating to velocities of 40 to 100 kilometers per second. Mercury's gravitational pull is so weak compared to the Sun's overwhelming influence that Mercury cannot normally capture objects as moons the way larger planets can. They get pulled past Mercury toward the Sun instead on hyperbolic trajectories. This is one of the fundamental reasons why visiting Mercury is so difficult for spacecraft that must fight the Sun's gravity. But that's not to say that Mercury can't stop such an object from reaching the Sun through collision. It just has to physically block it by being in the way. Yet, this explanation of high-velocity solar-influenced impacts cannot fully explain this last peculiar formation we'll examine. Take a look at one of the most fascinating and enigmatic craters on Mercury, Apollodorus, and its surrounding Pantheon Fossae radial graben system. At first glance, you might think there is nothing particularly unusual about the crater Apollodorus itself. Yes, those fractures running out from the centre are a little unusual compared to typical impact craters, but perhaps they're just normal radial fractures from the impact. But look more carefully at the entire structure. There are several features that are odd here that don't match impact crater geology. To begin with, the fractures emanating from the centre and the surrounding concentric and radial fractures bear a strange resemblance to fractured glass or ice, rather than typical crater ejector patterns. Glass fractures in this distinctive radial pattern due to its hard but brittle material properties. As you have seen throughout this exploration, most other craters we've seen on Mercury do not follow this fracture pattern at all. The crust of Mercury does not tend to fracture in this glass-like way, but instead produces ray systems through ballistic ejecta or just leaves perfectly round craters with rubble on the floor. This radial fracturing pattern is in keeping with a very different material behaviour from what we observe elsewhere. Sand does not fracture when impacted from above, but compresses and ejects. We do not see this type of fracturing anywhere else on Mercury's surface, either in thousands of other craters. So, something unusual is clearly happening here at Pantheon Fossae. Was the surface of Mercury particularly cold and brittle when this structure formed, thus making it more prone to fracturing like glass or ice? Mercury's nights can get as cold as minus 180 degrees Celsius in some locations, cold enough to make rock quite brittle. But if that environmental condition was responsible, why has this fracture pattern not happened in other places all over Mercury? About half the impacts should be hitting Mercury's night side, at least where temperatures are frigid, yet we see nothing comparable elsewhere. When we take a closer look at Apollodorus crater, the feature you might assume is the cause of all the fractures, we notice something even stranger that deepens the mystery. Apollodorus is not quite at the epicenter of the fracture system. While it's pretty close to the center, it doesn't actually line up precisely with the focus of the radial graben. This spatial offset might suggest that Apollodorus crater and the spidery fractures of the Pantheon Fossae are actually unrelated features that just happen to overlap. Whatever caused this dramatic fracture phenomenon may have happened first, only to be later hit by an asteroid near to but not exactly on its epicenter, creating Apollodorus. But if that's the case, what caused Pantheon Phocea in the first place? The intriguing thing is that we don't know with certainty despite over a decade of study. Evidently, something created this fractured glass-like pattern covering 40 kilometers but left no obvious crater at the center. Might that imply that this is the result of not something hitting Mercury from above in a typical impact, but something pushing its way up from beneath the surface? Perhaps this is the result of immense volcanic activity and magma intrusion, suddenly pressing up from Mercury's mantle and cracking the brittle crust like an eggshell being pushed from inside. That's just one hypothesis among several. There are still many mysteries to be solved about Mercury's surface, and many other fascinating insights to be gleaned as science advances and new data arrives. When ESA's Bepi-Colombo spacecraft arrives at Mercury in December 2025, it will begin another extensive multi-year study of the planet, with 2 spacecraft working in tandem, and perhaps then we will finally have the answers to these puzzles that have eluded us. Bepi-Colombo will uncover the characteristics of Mercury's magnetosphere and exosphere in unprecedented detail with dedicated instruments, and will take a clearer look at its geology and composition from 2 different orbital perspectives simultaneously. But until then, while we wait, scientists will continue to pore over the existing data we have from MESSENGER's 4 years in orbit, finding new patterns and insights. For now, Mercury endures in its extreme environment, baked in its solar furnace by day and frozen by night. It has survived there for 4.5 billion years, and will likely survive for billions of years more, in spite of all that the Sun and the solar system have to throw at it, including solar radiation, solar wind, micrometeorite bombardment, and the occasional larger impact. The hellish conditions of its environment make it challenging to get to for our spacecraft, but there is no denying its resilience shown in its charred, cratered beauty that tells the story of solar system history. Perhaps one day we will know all there is to know about the first of the solar system's planets, unlocking every mystery. But that day is not yet despite our progress. In spite of Mercury being the most illuminated planet in the solar system, thanks to its privileged location closest to our star, there is still plenty of light to shed on Mercury's remaining mysteries, and Bepi-Colombo will help illuminate those dark corners of our knowledge when it arrives at this fascinating world in just over a year from now.